Hello. Good morning, security fans. Welcome to the Rumsford Room. My name is Jen Janesco, and I will be the MC for the first two talks today. And first up, well, let's talk about the first talk so we can get rolling. Is everything in order? Yeah, everything good? Okay. So, as security professionals, we always know that there has to be a balance between security and usability. And the first talk today explores the challenge of usability within the space of multi-factor authentication. Now, we all know that multi-factor authentication is one of the best ways to prevent an attacker from being able to exploit just a simple password system. But you have to think about all of the different ways that you can do multi-factor, right? You have hardware tokens, you have apps on your phones, you have actual SMS. But there are all problems with that. There's a definite usability issue. And so today, you're going to hear a story of how when usability met to FA. And I'm going to have to read the list of the authors for this because it was a team effort for this. So it's going to be Hyun-Soo Kim, Juno Lee, Ki-Hong Heo, Sang-Kil Cha, and Myung-Gyeon Shin. This is a group from KAIST, which is the Korean Advanced Institute of Science and Technology. So sit back, relax, and hear the story.
Hey, thanks for the great introductions. Can you hear me? Can you hear me? I see. Great, thanks. So again, thanks for the introductions. And this is Hyun-Soo Kim from KAIST. In this talk, I'll present about how hard it is to strike a balance between usability and security, mainly in two-factor authentication. The title is When Usability Met to FA. And this is a joint work with a group of our team. And we are all from KAIST. And if you heard of KAIST, that's great. Otherwise, let us begin with introducing ourselves. So we're currently in Korea, far away from Munich, as shown on the map. And Korea and Munich are about 13 hours far away in a single hop flight. So considering ourselves as a physically distant party, we really appreciate having a chance to present in the event online. And the picture is an overview of our campus, where you can see many buildings and grasses. And this is a picture of blossoms in full bloom in the campus last spring. And this is the building that we are currently in with green lawn. Yeah, and KAIST is one of the leading research institute in Korea. So the name stands for Korea Advanced Institute of Science and Technology. The QS world ranking of KAIST is 41, which is moderately high. And especially in computer security, KAIST marks the 4th in Asia and 35th in the world. So that being said, one may imagine how tempting it is to launch a cyber attacks towards KAIST, as there are a bunch of classified experimental results and bleeding edge research in progress. Indeed, there has been and still happening attempts to exploit the ID service of KAIST. And some black hat hackers managed to leak the privacy information from library's electronic research node system. From the attack, more than 30,000 members' personal information were put in jeopardy. The incident was considered to be serious security breach, and the KAIST administration decided to enhance the security overall. So through the postmortem, KAIST decided to adopt two-factor authentication, that is the well-known authentication mechanism that requires two proofs to identify a single user. I'm pretty sure that most of you may have seen and already experienced how it works when you're using service from maybe Google or GitHub. The authentication mechanism basically requires two distinct proofs, where one is what the user knows, such as password or PIN number. And the other proof shall be what the user physically possesses, for example, your mobile device, bank card, or even a USB stick. While it seems quite trivial to adopt 2FA mechanism throughout the institute, The problem was to consider the usability of 2FA at the same time. Since KAIST members include aged professors who usually are not familiar with complicated procedures to log into a certain simple service, the fact is that they think 2FA comes with no good and merely harms the usability. The security team in KAIST had to come up with a secure 2FA that is also convenient to use at the same time. So here's how it works. So here we demonstrate how the invented 2FA system works, and they call it easy authentication as marked with red box. And all you need to do is type your ID, which is, for example, BSidesMunich rocks, which is obvious. Then click the button. Soon the pop-up window shows up saying the authentication is in progress. Then a push alarm arrives to the user's mobile device saying attempt for the easy authentication is being detected. If you click on the push alarm, the custom app is launched and asks for the Face ID or Touch ID immediately. If success, the user is authenticated. And yeah, that is all for demonstrating how the system works. And I'm pretty sure most of you may have already found out how sloppy the system is being designed. Then, about several months after the suspicious 2FA was launched, in KAIST Graduate School of Information Security, there was an exciting course going on called Binary Code Analysis and Secure Software Systems. As the name of the course indicates, students were expected to learn binary level program analysis techniques to achieve the end goal, which is secure software system. And those pro hackers around the campus who usually solve hard CTF problems as a hobby gathered to take the course. And one day, the instructor of the course, Professor Sang-Kyu Cha, announced the midterm, which was not simply testing one's knowledge. And the students were asked to find the vulnerabilities in KAIST Easy Authentication service. At the same time, he explicitly mentioned not to actually exploit the system at all. For the midterm, 24 hours were given to demonstrate the proof of concept and write a short report about it. And one of the pro hacker who was taking the course managed to hack into professor's account and submitted a screenshot showing oneself successfully got into the KAIST academic system as part of the report. And if he managed to do that, to do so, he could have manipulated the grades and so on. So the professor got embarrassed by the student, yet he was fairly satisfied with the performance of the students that they found many serious security threats of the system, much more than he thought. And here's the analysis of such vulnerabilities. So first of all, it is not even a proper 2FA. It's a single factor authentication because it only requires the proof of having a device. And the ID itself cannot be a proof for the authentication. And it's as we have shown in the demonstration, it's very vulnerable to human error. One can accidentally authenticate the unknown request by mistake, and it is impossible to review or retrieve the given sessions. And the other vulnerability that we found was the authentication, the whole authentication procedure could be bypassed by circumventing entire authentication process. And we found it being the most powerful attack. And the reason why they had this vulnerability is they had to implement a new 2FA system over the deprecated authentication design. And there was a misalignment between the two. And this huge and serious vulnerability was there. And we can, in later this talk, we will shortly demonstrate how this attack works. And not only those two, we were able to find other more serious vulnerabilities. For example, ID leakage, DDoS, which is distributed denial of service, and IDOR, that stands for insecure direct object reference. And ID leakage is the vulnerability that user ID validity check API was public, so that it can be abused as an oracle for valid IDs by an attacker. And by enumerating valid IDs, hackers can arbitrarily select their target victim. And that denial of service using botnet could also be done with IP spoofing that makes the tracking nearly impossible. And also, lastly, IDOR is an access to an unauthorized resource. And again, this was the other vulnerability that comes with misalignment between the legacy system and the newly implemented system. So basically, there were other vulnerabilities due to poorly designed architecture of APIs. So here's a short demo that demonstrates the authentication bypass attack. First, the attacker can enumerate user IDs by going into the KAIST mail service, where you type in some string there, and it shows you the match of that string to certain KAIST members. For example, here we find Myunggun's ID, basically email address. And the finding is that most users have the same ID with the head of the email address. So we just use the head of the email address as an ID for the attack. And then we try to authenticate the user in the browser. And with proxy, for example, Fiddler, we intercept the login packet and then replace the login packet with the custom string that we manually find out. And by replacing it, one would successfully log in with victims authentication without knowing the password or having a device. So here's our suggested solutions to the institute. First, we strongly mentioned that rollbacking the password auth would be the trivial and most definite solution. And after that, although it needs the further backup solutions, but we were very clear to say that this must be done right away. But they didn't, but they rejected because of institute issue. And then we tried to suggest, we also said the original system itself is not a 2FA, and we have to go with proper 2FA that has to come with a password and device check altogether. And it was funny that there was already another service in KAIST, which is KAIST VPN service, that already comes with 2FA. And it requires you to enter password and one-time password via device together to get yourself authenticated. And then we also suggested to have session review and retrieval functionality in the system. So if you have, you may have seen this functionality in GitHub or Google, so that you can review the currently activated sessions, so that you can list up all the current sessions that is going on, and then you can selectively retrieve those sessions which seems to be spurious. For example, if you're in Germany, but you somehow found that some session were said to be in Korea, you may think that it's very spurious, right? So that you can retrieve that session. And then we had several iterated meetings with KAIST administration to get the system fixed, but they rejected they were pretty against with our suggestions because the issue was usability. I mean, they agree with security issue, but as we go with proper 2FA, it kind of harms the entire usability so that they cannot go for it. So with the suggestions, we kept on suggesting other measures to make it secure through the several meetings with the security administrations. The only change they made was to pop the number up on the screen on both the browser and the mobile app. And so that the user, before granting access with Face ID or Touch ID in the mobile app, the user would hopefully check if the number shown on the app matches with that of a browser, so that the user won't mess up with, mistakenly authenticate other requests or attack by a certain hacker by mistake. And it partially mitigates the vulnerability as it helps to confirm which access is likely to be malicious or not. And some may ask if can this be said to be understood to be fixed solution? And definitely it's no. So in conclusion, our takeaway message is as follows. First, implementing easy-to-use 2FA without weakening the security is very tricky. So, as we have seen in the last slide, the improved version is still not a proper 2FA. And second, software testing and formal verification should help in its proper design. And the two methods are traditional yet effective ways to find bugs and guarantee the desired software property. And here's the references for our work. And thank you for listening. If you have any questions, please feel free to ask.
So, do we have any questions for our speaker today? One in the back. Morten is going. He's going.
Testing. Seems to be working. Hi. On the issue of usability versus security versus usability, there's several systems that don't require user input, but you just talked about just having proof of a USB stick you put in. What's your stance on FIDO2 tokens and stuff like that, where you don't have to input anything, but it's just there and you just have to attach it?
Sorry, I cannot understand you.
Should I repeat? I'll try. What's your opinion on passwordless login procedures through hardware tokens in the security versus usability issue?
Security token. Password itself is not a. It is a traditional way to authenticate, but it is also traditionally known to be unsafe, right? Because password only is very error prone to human errors, and using USB stick is, together with USB stick, you can achieve better security, I guess. That for sure. Am I getting your question right? Or am I missing?
I think part of the question is, so when you have a security token on a USB, for example, what role does usability play there? Is it easier? Is it less easy? Does it make it better for users if they just have to use one of these security tokens? Or
you mean is security token? You mean the number shown on the screen?
Nope, we're talking about there are USB devices that have basically set it up so that using cryptography, you can plug it in and basically identify as yourself. And so that's commonly used as a form of authentication. And so in that case, a person only has to have this hardware authentication and then their login and password, of course.
Oh, I see. And how does that come with usability?
Correct.
Is that the question?
Yeah.
Oh, I see. Oh, and I think that's a good question. But I think if you have USB stick, you may have hard time using logging into the certain service through your mobile device where you cannot easily plug in the USB stick, right? So I think that kind of harms the usability still if we go for USB stick. Will that answer your question?
Yep, did that answer? Okay, we got a thumbs up, very good. So any other questions for our speaker? I'm checking the time. I actually have a question for you, and that was bad feedback. So you said that there was an entire team or an entire group of people looking at this in a class. And I'm wondering, what kinds of tools did you use to investigate the implementation of multi-factor?
Oh.
You mentioned Fiddler. Yeah, go ahead, sorry.
Yeah, Fiddler was the option. And I only used Fiddler. I have to ask other team. And basically Python script.
Okay. And then my final, so the class that you were taking, though, focused on basically finding vulnerabilities in code. So what kind of tooling do you use in that course to actually find vulnerabilities in code?
Oh, yeah. We use IDA Pro, for sure. Ghidra, and GDB, of course. Yeah, I think that's all. And and we write our exploit with Python and using Pon. I cannot recall the name of the library right now. But.
Okay. And then for the solution that you analyzed, was it, I didn't get at the beginning, was it a homegrown solution? So,
yeah, right.
Yeah, okay. Would you ever recommend to build your own multi-factor solution, or should you just buy it off the shelf?
I think it's, I would buy it off the shelf because, it's very trivial to satisfy the 2FA property so that you won't get any additional benefit by having it yourself, unless you have a very clear idea that can, balance, guarantee other property such as usability here. And yeah, if the purpose is just for security, I would buy it off the shelf. But if you do it something more fun, I'll definitely go for myself.
All right. Does anyone have any other questions? Okay. Then thank you so much for your time today. It was great to hear about your story, and have a great rest of your day.
Thank you.
If you're looking for the live stream, then look at the Discord server.
Hello. Oh, I didn't expect it. Wasn't expecting the microphone to be on, so now I know that it is. Carry on. We have just a few minutes. If you're here for keeping electric cars secure, you're in the right place.
So it looks like we're all set up. You have 2 minutes.
I'm going to start talking at 29. Welcome, security fans, back to the second talk in the Rumford Room. Once again, I'm Jen Janesco, and I'll be the MC for the second talk. I'm going to start the time now. So, first thing, if you have questions at the end of the talk, which we will have time for questions, I would like you to run to the front of the room and talk into the microphone so that everybody can hear and also our speaker can hear. Okay. That being said, let's get started. So, a few years ago, there was this guy, his name was Charlie Miller. He hacked a Jeep, he made it really, really public, and everybody learned about the CAN bus in automobiles. But that was a gas-powered machine. How has the CAN bus evolved in the world of electric cars? Our speaker today is going to talk about exactly this and a few other things. We have with us today Shivaranjini Sankaralingam. She has a master's from Carnegie Mellon, and she's working as a security researcher at Dll SV in Singapore. And she's speaking to us today live, but remotely, to give us a talk about keeping electric vehicles secure and the need for a CAN security framework. So give it up for Shivaranjini.
Thank you, everyone. So good morning. So my name is Shivaranjini, and I'm going to be talking about my experience on keeping electric vehicles secure by proposing the need for a CAN security framework. So a little bit about me. So as the MC has already mentioned, I'm a security engineer with Dll SV Singapore. And we have a global presence, and there's also a division right there in Germany. We specialize in smart cabins, in smart driving, including self-driving capabilities, and we have over 35 years in the automotive industry. So before working in the SV, I had a short stint at National University of Singapore, where I got the chance to hack into one of these famous yellow Bluetooth bikes that you see in the picture right there. And I was able to hack into them and was able to ride it without having to pay for it as a part of their bug bounty program. That got me super excited about vehicle security. And then I transitioned from bikes to cars, which is my current focus. I also have a master's in information security from Carnegie Mellon University. And for fun, I play a musical instrument sometimes. And every weekend, you can see me paddling along the Klang River in Singapore. So today, I'm going to be starting with an introduction of what is CAN and the security challenges that come along with it. Then I'm going to be walking you through my journey of developing an intrusion detection system over the years through different phases, and what are the lessons I've learned along the way. And finally, I will be proposing a CAN security framework that addresses some of the problems that I've encountered so far. So let's start with CAN. So what is CAN? CAN, or Controller Area Network, is the main communication channel inside an electric vehicle, or the crux of an automotive system. So it connects all the important components that you can think of, like cruise control, brake system, air conditioning, gateway, you name it. So everything is connected through this CAN bus, and these components are called as electronic control units. And CAN is the channel that connects them and enables the communication between them. So the main benefits of using this protocol is that it's inexpensive, it's durable, it's very lightweight and reliable, and it's also broadcast-based, unlike peer-to-peer based, which means that it has much less overhead. And that's primarily one of the reasons that electric vehicles use CAN as one of their major communication channels. So a little bit of a deep dive into a CAN header or a CAN frame. So you can see a number of fields there, but there are three key fields that I would like to highlight. One is the arbitration ID. The other one is the LC, which is the data length code. The data length code is basically gives you the number of bytes of payload of data that follows along with it. So here we have to 8 bytes of data. So that would be the DLC, which indicates how much of payload is sent along in that CAN frame, and the time at which the frame was itself sent and the data itself. So the key feat here is arbitration. So let's start with that. So in an electric car, we have many electronic control units that want to talk to each other. And they have this CAN bus, which is their communication channel. So each electronic control unit has a specific set of message IDs that is always on the lookout for. And once it encounters that message ID on the CAN bus, it reacts to it and starts a communication with it. So since it's broadcast-based and many of the electronic control units would try to do this simultaneously, the CAN bus has a process called arbitration, which gives priority to which message can be executed first. So if you have a lower message ID, then you have higher priority. So by logic, if you have 000, which is the lowest you can go, then your message would be given the highest priority and would be executed first on the CAN bus. And every other message has to wait a bit more. So this number is represented by the 11-bit arbitration ID as referenced here. So a little bit more into the different type of CAN messages. So we have 2 broad classifications. One is called the periodic messages. So the periodic messages are message sent periodically to get the statuses of different electronic control units at different times. So I'm an ECU A and I want to talk to ECU B and I want to know the current status at this particular point of time. So I just sent messages periodically to know, hey, what's your current status? So that kind of messages is periodic. So the second type of one, which is called as event triggered, is messages that only occur when a particular event happens. So someone locks the door, someone unlocks the door, you apply brakes on the car. These kind of events that are happening will trigger a bunch of messages that are only pertaining to that. And those kind of messages are called as event-triggered messages. So if you see the screenshot here, this is from a CAN database file. You can see 2 words that comes up very often. One is cyclic X and the other one is spontan X. So anything that's called a cyclic refers to the periodic messages. And anything that's called spontan X, which is much, much fewer than the cyclic X messages, refers to the event-triggered messages. And you might be wondering, looking at the screenshot, what is this X and why is there a CAN extended written at the end of it? What's the significance of it? So the X refers to an extension or an extender, and it's called as CAN flexible data rate, which allows you to send up to 64 bytes of data and has a longer identifier. It basically allows you to send more data in a single CAN frame as opposed to the original classic CAN. So what does this mean from a security perspective? So historically, when CAN was introduced by Robert Bosch in 1983, it was only meant to be like a very lightweight, reliable mode of communication. And there is no authentication or authorization that is built into the protocol itself. So in order to ensure security, you have to take additional mechanisms. So one such mechanism is building a model or component that will do the authentication or authorization for you. So coming to that, You have one such examples of the model is in AutoSAR's SecOC, or Secure Onward Communications. So basically what this module does is, as referenced by the figure, it generates a lot of message authentication code and freshness value, which is used to authenticate the electronic control units communicating on the CAN bus, and send these keys plus data in the CAN frame which allows you to send more data. So if you're using a classic CAN, sending this type of information would mean that it will not leave you space for anything else, and it's not your best bet. But CANFD can allow you to send your security related data as well as the data it's originally intended for. So, but there are two challenges that come along with this. One main important one is that you have to secure the keys itself, safeguard them. And the next important challenge is that SecOC has 2.5 times more bandwidth than CAN itself. So in certain situation, which means that you cannot use this always, because you would have to sacrifice your bandwidth for security. And we don't want that, do we? So what other option do we have to ensure that there is security and the CAN bus itself, the communications is secure? So here comes intrusion detection systems. So many IDS solutions sit on different electronic control unit components and monitor the messages along the CAN bus. So an example could be Gateway, which can look at messages coming in from different electronic control units. So there are broadly two very different type of IDS pertaining to CAN. One is flow-based, which only needs the bare essentials. The bare essentials meaning the message ID and the time at which the frame is sent. You don't need the data, you don't need anything else. So this kind of information, this kind of flow-based IDS is useful because it's very generic and you can use it almost in all the vehicle models that you can think of, because it's very generic. It's not data specific, it's not vehicle specific. So once you develop an algorithm, you don't have to go around changing it again and again. Whereas packet-based focuses completely on the data packets or payload itself. So this is also useful in certain situations. So these are the two major types, and hybrid is a mix of both of them. So when I started to develop an intrusion detection system, I started with a prototype. So my goal was to create a working prototype from data that is publicly available. So I wanted to identify common attack scenarios and generate attack scenarios pertaining to that. And along with my team, we wanted to add some machine and deep learning features to this prototype. And finally, test the results on a PC to see how our IDS algorithm has fared so far. So upon a lot of literature survey, I came upon a very highly cited academic paper called OTIDS, which proposed a novel intrusion detection system from the HCRL lab in Korea. So they had 3 common attack scenarios, which is denial of service, fuzzy, and impersonation. Their data was publicly available, which is kind of hard to find in automotive domain. The algorithm itself was fairly easy to implement. And so this seemed like a good reference point to start off my prototype. So I wanted to generate more such data. So I used Vector Scanoi Network Box. It's basically a simulation tool. And I used this and programmed more attack data sets based on the reference model that I have with me. So some of the attack scenarios, the first one is denial of service. So as the name suggests, the goal is to either jam the CAN bus or try to get the highest priority on the canvas. So the way to do this is to inject messages that are the highest priority, which in case would be 000, which is the lowest you can go. You just try to just like spam it in a very short period of time. So either you get the highest priority or the canvas becomes invalid. Either of this becomes a denial of service attack. The next one is fuzzy. So it basically is a spoofing attack where it injects spoof random CAN ID and data values. So for example, replay attacks is a common example of a fuzzy attack. So, and a few other examples could be, you have the right payload and data, but you send them in wrong timing. So you have a time that is expected in a normal scenario, but then you just send it along in a different timing. And another one is you have the wrong data, but then you send it in the exact sequences that is expected in a normal scenario. So these are all examples of a fuzzy attack. So the data format that was followed in this model was a request response model, where the request was identified with a data length code of 0, and the response had a data length code of either 4 or 8, and it had the same ID, so we can recognize that it's a response, and it came along with a payload after that. So the data was collected from a Kia Soul vehicle, and for the fuzzy attack, the authors had 2 responses, and they randomized one of it as original and the other response is attack. So I graphed the packets as they arrive, if you can look at the figure here. And so any packet, any response that arrives after the 7th message is considered as a lost packet. So we only considered that particular window as legitimate ones. And from the figure, in an attack-free state, most of the packets, even if they arrive late, they arrived at a pretty good time interval. It didn't take too long of a time to get the response to arrive. But if you look at denial of service and fuzzing, when I graphed the arrival time, you can see that they significantly increased in both these scenarios. So here you see 000, which means an attack is happening, and the response came much, much later. And in fuzzing, as I mentioned, there's 2 responses, and they randomly chose this to be the legitimate one. So as usual, you can just look at the graphs. You can just see, oh, there is something happening. There is an attack that's happening here. You know, it does not look normal, or it does not look like it's in an attack-free state. So that's a very good indicator. So with the help of my team, we added more machine and deep learning features to this model and tested it. And it came from 85% to 94% on the PC, which looked good, right? The numbers look good. But then I realized one thing: they didn't mean anything. When I requested data from the original equipment manufacturers, I realized that most CAN data, they do not follow the message request format at all, and instead follow the sequencing format. So which means what I had implemented was a corner case scenario and not the norm. So one of the biggest takeaways that I got was to never trust the research scope blindly, even if it was highly cited research. So it was back to the drawing board. So this time I wanted to create a proof of concept, and I was very careful to model the attack data based on real industry data. And instead of testing it on PC, I tested it on IQ03, which is to say is high-powered ECU. So this ECU is mainly used for autonomous vehicle capabilities. So the attack scenarios were similar to the prototype ones, the denial of service. And for fuzzing, I also included the categories of CAN messages into account. So for fuzzing, I send packets that model the original one, but it's injected in a timing that is different from what is expected in a normal scenario, and it applies to both the periodic and eventual messages. But for frequency, it's essentially the same as fuzzing, but it only applies to periodic messages and not even triggered messages. I also added an additional attack scenario, which is any ID which is not recognized by the original equipment manufacturer is also considered as an attack packet. So I labeled that as alien ID. So this was the model for the proof of concept. So I would have the normal data set, and there would be a pre-processing algorithm that would understand the how it behaves in a normal scenario. So once I knew that, we generated attack data sets using the Canoe vector box and fed it into the IPU. This is the IPU03. So there were two detectors which are part of the intrusion detection system. The first one is a logistic detector or a statistic-based algorithm, which takes really less resources and weeds out common attack scenarios like denial of service and alien ID. The next one was a learning-based detector, which used a deep learning-based algorithm to filter out the fuzzy and frequency. Eventually, it will just give out if it's a 0, which is a normal, or 1, which is an attack. So the results looked something like this for these statistic-based ones. So for the alien ID, it's anywhere from a 98 to 100%, which is really, really good. And for the denial of service, it was either 82 to 83%, which seems really good and is very comparable to the industry standard. So if you combine both of them, the accuracy goes a little bit up to closer to 91%. So this seems pretty good and in line with what I had wanted. So for the deep learning algorithms, it ranged from 85 to 98%. And the screenshot here is from IPU03 once the deep learning algorithm was executed. So it just says that the accuracy is 100% here for that particular data set. And it just gives you some statistic of the messages that were being processed. So what were the challenges that I encountered during this phase of proof of concept? So the first one was to fit the statistic-based algorithm into the MCU, since it takes up very less resources, and to weed out the common attacks like DOS and alien ID. But then I found out that there was no straightforward way to get the ID and timestamp in IPU03 because of the way that it was designed, and I needed to make some changes on a deeper level in order to be able to do that. So, and the second challenge, which you might all have guessed, is that we need to make sure that the intrusion detection system is not the sole focus of the issue itself. So it should not take up a lot of the resources, be it if you put it on system on chip or if you put it on MCU. It has to perform very well and take up very little resources as possible. So the proof of concept was a fairly good success, but this brought me to a very important question. And the question was, I used data sets which are simulated, and the IDS algorithms did really well on them. So that's great. But that does not equal to a real car. So if you actually deploy these IDS algorithms in a real car, would it still work the same way as it is intended to? Because in a real car, you can have some latency, some delay, some legitimate packets can come later than they're expected to. And what happens to the IDS algorithms then? Would it still perform as it's supposed to, or would it give you a lot of false positives and false negatives, which we want to avoid? So in order to answer the question, I proposed the CAN security framework. So I wanted to set up a CAN test bed, which can be used to run a CAN bus in a realistic environment, and then develop a pen test tool, which can inject messages into the CAN. So this is basically this would be like an attack toolbox that injects messages into the CAN testbed in a live environment. So one of the main outputs that you can get from here is a very realistic attack data set that can be fed into the IDS algorithms. You can see how the algorithms fare. You can make modifications if it's not up to expectations, and then you can again feed it over here. So it's like a continuous loop for improvement of security. So an example, just a very example of a CAN testbed setup is I have a wired CAN harness setup with a lot of nodes. And then, some of which is uses Arduino and simulates different components in a car, like a door, engine, HVAC. And then there are some nodes which have the much advanced ECUs from Dll, like IP03. So, and some nodes which are left open, so we can add more ECUs later on when we want to continue testing. And this connects to a USB to CAN interface and then connects to a PC, which runs the software message injection toolbox or the pentest toolbox, which performs the attacks needed for intrusion detection systems. So you can also have other related components for the ECUs to work, like sensors or actuators and other platform environments to make this run smoothly. And so the pentest toolbox itself would start off with emulating denial of service attacks, fuzzy, replay, or man-in-the-middle attacks, then the frequency attacks by manipulating periodicity, and to be primarily developed in Python. So with this, I'm going to go to the end of my presentation. So here are some of the key takeaways that I want to share with you. One is that if you have a highly cited research, it doesn't always mean that it's useful in the industry. So always model a system based on real data. And my opinion is that hybrid IDS is the best bet moving forward. This flowchart here represents a model for my proof of concept, which took up very less resources. So I had a statistic-based algorithm which weeds out most of the attacks, and a deep learning one which weeded out the advanced one. So if companies want to do something more specific for payload, it can be just added to this model over here without compromising on the resources, which means that it would be a really good solution, in my opinion. And finally, I do not consider my prototype to be a total failure because I got a chance to be here and tell you what not to do. So with that, I would be ending my talk, and I'm open to questions now from the audience.
Hello. All right, folks. So it is question time. Does anyone have any questions for? Oh, we have a questioner. Come up, please.
Hi, I have a question related to your IDS model and related to your OEM data that you received. So isn't it like that you probably have to train a model for each different type of car model because the data will always look different, maybe even inside the same OEM model line?
Okay, yes. So basically, if you use a flow-based IDS, which is what I do, the IDs would be different for each vehicle model because each OEM have different IDs and different way of processing them. But the logic itself would be same, but you have to, as you're right, you have to retrain it for every single model, depending upon their own IDs and specifications, but the core algorithms would remain the same if you use a flow-based model.
Okay, thanks. And question 2, if you don't mind.
Mm.
In the very beginning, you were talking about using message authentication codes for protecting CAN bus messages. How do you actually distribute the symmetric key for that?
How do you what?
How do you distribute the key that is used for the HMAC for the MAC?
This key is distributed along the the extended can frame. So it is sent along with the frames. When you do the checking, you would actually check if it works or not on the receiver's end. So it's sent along, it's distributed along the can frame itself.
So how do you secure those messages with the key?
Let me just go back to the slide. Okay, so you have a sender and receiver side. So you basically have you generate a MAC, and then you have on a receiver side, you would verify the key that is being sent. So I think like you would send this on a CAN FD, and you would like, based on the agreement before, you would just verify. And if it's not okay, then you know that someone has tampered with the message. And if it's okay, then you would proceed with the other functionalities.
Right, but where do you get a secret key from?
Oh, okay. So I think this is, I'm not really sure, but I think this is randomly generated. This is something I do not completely know yet.
Okay, thank you.
All right. Are there any other questions today? So then, with that, we're going to close the session. Thank you so much for being here, Shivaranjani, and have a great day.
Thank you.
So folks, I think, is there a break right now, Morton? There's a break, so head out, stretch your legs, get some air, and come back for some great talks.
Hello. So we start exactly on time. Hello, everyone. Nice to meet you all here in the Rumford room or in the Moonshot stage. My name is Oliver Nettinger. I'm emceeing the next block. And I'm very happy to introduce to you today Sarah Mader. She's having her talk about Bluetooth low energy devices and how to, I would say, hack them. And yeah, I think it's a super interesting topic because probably everyone in the room has at least one device that supports Bluetooth low energy. And as I've heard and got to know, it's not a very simple protocol, and the specifications seem to be pretty insane. So I'm very much looking forward to learn about Bluetooth low energy hacking today. And please spend a warm applause for Sarah and enjoy the talk.
Okay, hello, hello everybody, and welcome to my talk, Hacking Exploit Development for Bluetooth Low Energy. Let me first introduce myself. My name is Sarah Mader. I'm a security analyst at Inside Attack Logic, whereby my main fields are IoT and hardware hacking, web and network penetration test, as well as the Bluetooth technology. A few words to my company. Inside Attack Logic was founded 2014 in Munich, where we also have our headquarters. We are doing mainly offensive security, so red and purple teaming, penetration test, as well as security consulting. So Bluetooth low energy. What is this? Do we need this? Is this important? If you have a look at this diagram, which is provided by the Bluetooth SIG, the special interest group, in the yearly market update, this Bluetooth Special Interest Group is responsible for publishing and maintaining the Bluetooth specification. And if we look at this diagram, then we can see that they estimate a total of of over 5 billion Bluetooth low energy devices in 2022. And if you compare this to the world population, which is over 7.9 billion people, then probably it's quite an interesting topic. And most of you at least have a smartphone, which I assume to be Bluetooth capable. So what's about security? We can divide the vulnerabilities in Bluetooth in 4 categories. There are general flaws, which relate to every wireless protocol, as also Wi-Fi, for example. So everyone can send packets over the air, so jamming a connection and denial of service attacks are very easily to realize. The next big problem is our configuration issues. So simplified that, if you do not use any encryption, then it's probably not secure. A big problem for the protocol itself are design issues. In the beginning of the protocol, you might already have heard about the talk from Mike Ryan, with low energy comes low security. So the earlier version did not provide any security in the pairing at all. It's still in the newer versions, which try to, we will come to this soon. Still in the newer versions, many vulnerabilities were discovered and published, and I think the last one was at the end of last year, which I know about. And finally, we have implementation issues, and implementation issues can lead to very serious vulnerabilities. There's one very impressive example, the bleeding bit vulnerability, which was discovered by the ARMIS research lab. And hereby, the researchers detected a heap-based buffer overflow and the handling of advertising package, which lead to code execution and finally could lead to network compromise of the connected Wi-Fi network. I added the sources for reference. So getting started. If you start with Bluetooth low energy, you might you have at first the Bluetooth specification. which is a very large document. The Bluetooth specification, the newest version 5.3, is over 3,000 pages large and is quite overwhelming if you start. Nevertheless, we have not the time to dive in that deep today, but I will give a short overview of the techniques we need for the later exploit. After this, we will discuss our attack scenario, have an overview of the Mirage Framework, which I prefer to use for my exploit development, have here some implementation details, and finally we have our demonstration and the conclusion. If you start with Bluetooth, you have at first to know that Bluetooth has its own protocol stack. The protocol stack is hereby divided into host and controller. The host layers are marked here in blue, are regularly implemented in the host operation system or your smartphone, and the controller layers are separated in hardware. So if you think, for example, the easiest example here is if you have a Bluetooth USB dongle, then the controller layers will be implemented in this dongle, and the host layers are implemented in the host operation system. The host controller interface is then implemented or realized via USB. Might also other interfaces are possible. The most important layers for us here are probably the security manager. The security manager is responsible for the security in Bluetooth, mainly for establishing a long-term key and further distributing encryption keys, or, for example, keys for address resolution. And the second layer which is involved in security is the link layer, which uses this previously established key for the final encryption. So we can summarize the connection setup as follows. We have always two, or in most cases we have two parties in the protocol, the master and the slave device. The master device is usually your smartphone or your computer, and the slave device are peripheral devices, as for example keyboards or smart light bulbs or any other smart IoT product. These slave devices send advertisements to make itself discoverable for the master device, and the master device will then scan for these advertisements, and if this is the correct slave device to connect, then the connection request is sent, and the connection on the physical layers are established. And after this, we have a service discovery. So every slave device offers services for the host, for the master device to use. And if one of both devices decides that it requires a higher security, then the pairing process can be started. So pairing in Bluetooth depends at first on the version of the protocol or of the hardware, which version is the hardware is capable of. And the other factor are in and output capabilities. In and output capabilities are, for example, displays or keyboards. The earlier versions were the legacy pairing, so 4.0 and 4.1. Here we have just works, passkey entry, and out-of-band pairing. Out-of-band pairing, we won't discuss it today because out-of-band is everything but it's not using Bluetooth as a protocol. Just works pairing is, as the name says, just works. So the user has no further, here's no further interaction from the user required. And for passkey entry, at least one device with a keyboard and one device with a display is necessary. So here, the display device will present a PIN code. I assume you already know this procedure if you paired a Bluetooth device earlier. And on the keyboard device, you have to insert this pin to finish the pairing process. This legacy pairing is very broken, and I already mentioned the talk, with low energy comes low security and should no longer be used. With version 4.2, the secure connections feature was introduced. Secure connections are based on an elliptic curve Diffie-Hellman key exchange, and also offer the just works and passkey entry pairing as well as out of band. And additionally, here we have the numeric comparison pairing. And numeric comparison means that we have two devices with a display, and on both devices the same pin will be presented, and if the user compares these pins, it verifies that the pins are identical, then the pairing is complete. Here we have to say the just works pairing is an unauthenticated pairing, so the just works pairing has no protection for man-in-the-middle attacks. Okay, so reverse shells are very good in Bluetooth hacking, so we have to do something other funny. And what is widely accepted are these Bluetooth keyboards. And I have to state here that this is not manufacturer related, it's just an example. This flaw relates to the specific service specification. So in this case, the human interface device service. And what we can do here, we can man in the middle such a Bluetooth keyboard and turn the legitimate keyboard into a rubber ducky device. If we do not know what a rubber ducky is a malicious USB stick. If once plugged in the victim's computer, is able to lock or inject keystrokes to execute commands. So for our example, we will refer to the rubber ducky language, the ducky script, and try to exploit the victim computer with a very simple example, which just pops up the calculator. So to achieve this man-in-the-middle situation, we have multiple options. The first option is, as already stated, we try to use the just works pairing, which is unauthenticated, and man-in-the-middle setup is very easy to establish. For this, the attacker requires two Bluetooth dongles, one for the connections with the slave device and one for the connection with the master device. And the attacker will present to both directions that has neither in nor output capabilities, and as a result, the just works pairing will be used if the devices accept this. The second option is if you say, okay, I know downgrade attacks, I would never connect my keyboard if I do not have to insert my pin code. Then we have a second option with the human interface device service. In this scenario, we first pair with the slave device, with the just works pairing. The keyboard often does not have the requirement to do an authenticated pairing process. And then we pair with the master, we spoof the device, wait for the master to connect, and allow the passkey entry pairing, because we say, okay, we are a keyboard, we have input capabilities, and as soon as the victim inserts the pin, on the master presented pin to the keyboard, it will be sent to our attacker device as regular keystrokes, and therefore we can use these keystrokes for the passkey entry pairing. So what do we need for this attack? We need two USB dongles. I prefer to use the NRF 58420 dongles. They cost around about €10 and are supported by many frameworks and are therefore very flexible. I use them with the Zephyr project. Here we have a host controller interface USB sample, which is at the end a Bluetooth USB dongle, then, if you want to say it like this. For the host layers, I like to use the Mirage Framework. The Mirage Framework is very complex, but also very flexible, and therefore does fit the needs for the Bluetooth protocol, which is also very complex. So as the author states, the Mirage Framework is a powerful and modular framework dedicated to the security analysis of wireless communications. The Python framework supports multiple protocols, for example, Bluetooth Low Energy, Wi-Fi, Zigbee, or infrared. And we have a closer look here. The Mirage framework has several components. There are at one side the core components, which are necessary for configuration, loading, and execution of modules. We have the internal libraries, whereby the Bluetooth low energy stack is implemented, for example, and we have modules and scenarios. We will focus on the modules and scenarios today. Modules offer the possibility to implement a specific attack, for example, the man-in-the-middle attack, and can be used by multiple scenarios to adjust this attack to our needs. So we have one module and multiple scenarios and can easily modify this man-in-the-middle attack to our needs. To do so, we have to define scenario signals in the module. That means every scenario signal stands for a packet that the module might receive. In this example, the packet is called say hello. And if the scenario want to override this method or this packet, then it would have to override the hello world method. Additionally, we can control if the module code is executed. So if the scenario signal method returns true, then the module code is also executed. And if the scenario signal returns false, then the module code will be skipped. To create a module in Mirage, we can use the command line option create module. This will create the following template. Here we have two methods which are very self-explanatory, I think. We have init, which initializes the module. Here the most important thing to note are the arguments. So we can pass some command line arguments to our execution. Most important, for example, the target device address and the host controller interfaces which are used by the module. And we have the run method, which is used for the final module code. So since the module for the specific example, so the secure connections man-in-the-middle model, is very large and also complex, and I also had to implement the cryptography for the secure connection in Mirage. We cannot cover this in detail here, but I will give an overview what the module does. So at first, the attacker will initialize both Bluetooth devices, Bluetooth interfaces, and scan for the provided slave device, also for the Bluetooth device address, and tries to connect earlier than our original master device. After this happens, most devices are blocked because slave devices usually are only capable of holding one connection at one time. And the legitimate master is no longer able to detect the slave device. After this, we clone the slave device, wait for the master to connect, and pair with both sides, depending on the scenario and the requirements. After this, the man-in-the-middle setup is complete, and the module is only forwarding packets from master to slave and from slave to master. So we will have now a deeper look into the scenario. The scenario can be created nearly the same way. Here we have three methods: on start, on end, on key. On start and on end are very self-explanatory again. On start is executed when the module starts, and on end is executed when the module ends. And on key is executed if any key on the attacker keyboard is pressed. So, since we want to pass our human interface device keys to lock the final user input to console, and also we have to pass our ducky script here. We will do this in our onStart method. The Mirage Framework provides a ducky script parser function, which is very comfortable. So we can provide our file here and have 4 callbacks, which I will explain on the next slide. On end can hereby be ignored, it's very trivial. And on key just says if we press the escape key, then we end this module, and if we press 1, we want to inject our ducky script to the established man-in-the-middle connection. The best way to explain this method is if we compare this to our Ducky script. So at first we have the add keystrokes method, which is most important. So here we have, so for human interface devices, it works as follows. So if you press the key on your keyboard, then the signal will be sent for the key. And if you release the key, then the keystroke release message will be sent. And what is most important here is the timing. So if you are too fast, or if you are sending our keys, our messages too fast, then some of our keys will be skipped. And if we are too slow, then the user can see every single letter appearing on the screen, which is a bit obvious. In the packet list, just is the array add delay adds the delay, or is for the delay parameter of our Ducky script, and add text is for the text, for the string parameter of our Ducky script. So one last thing to do. Since we want to log our keystrokes, we have to override the onSlave handle value notification packet. In Bluetooth, these keystrokes are sent via notifications from the keyboard to the computer. And here we check for the handle hex 13, and if it's the right packet, then we log our keystroke to the command line. So one last thing. The used keyboard for this example requires the user to push the button on the backside to put the device in advertising mode. So the device is regularly not in advertising mode, but you have to push the button if you want to connect this device. I will get to this point after the demonstration. So I hope to stop this here. Okay. So what we can see here is on the left side is the victim Windows operation system. On the right bottom, we have the Bluetooth keyboard, and on the right top, we have the attacker terminal, whereby the Mirage Framework is called, with the Bluetooth secure connection man in the middle module. We are providing the Bluetooth device address. The Bluetooth device address can easily be sniffed, for example, with the Ubuntu or also with Linux utilities, as for example, Bluetooth CTL. This device, is a funny fact, uses a random address, and the randomness of this device is that the force bytes of the address is regularly increased by 1 bit. So, okay. Then we have our interfaces, host controller interface 0 and 1. We do not require master spoofing in this case, so that the keyboard does not care about who's connecting. But we need slave spoofing so that the computer holds the keyboard for a regular Bluetooth, for the regular Bluetooth device. We provide our scenario, so Bluetooth Low Energy human interface device man in the middle, and finally we provide our Ducky script. Okay. Okay, that's good. At first, we are entering the scan stage. So, okay, this is very bad. Sorry. Maybe I can start. 1 second. Sorry. How is this? So maybe this is better, hopefully. Yes, okay. So we're entering the scan stage. Now the moment is here to push the button on the background of the keyboard. After this, the keyboard will be detected, connected, and cloned. And now we are waiting for the master device to connect. So master is connected, man in the middle stage is established, In the background here is now the service discovery that takes some seconds, and now the Bluetooth keyboard is connected. We can check now that our keylogger is working. And this keylogger is also working if the window screen is locked, so we can also capture the login password of the user. And finally, we can inject our Ducky script by pressing the one button on the attacker keyboard and opening the calculator. Okay, so a few thoughts here. How easy is this? You could say, okay, if this attack is only possible if the devices are not paired. Well, there are many ways to disturb the connection and enforce a new pairing process. So the easiest way I could think of is I just jam the connection, and as soon as the user is annoyed enough to repair his device, I'm able to intercept this connection. The next question is what you can ask yourself: would you push the button if your keyboard is no longer working and repair the device? I think I probably would. And to prevent this attack, you have to make sure that your keyboard provides security mode 1 level 4. This means that the secure connection mode is enforced, so that both devices enforce that an authenticated pairing algorithm is used. So not just works pairing, and then this attack is no longer possible. Okay, that's it. So, questions?
Cool. Thank you very much, Sarah. Round of applause for a nice talk. I think it was really interesting. We have some time for questions. If you have a question, please run to the front, to the microphone, and.
You named it Bluetooth low energy. How much of those attacks also applies to Bluetooth regular energy?
Regular.
Specific low energy specification of Bluetooth.
Well, the Bluetooth class specification also has unauthenticated pairing. So it's also called just work. So the specifications are not identical, but the pairing algorithms are comparable. And if your keyboard allows this unauthenticated pairing, then you also have the problem.
You mentioned that specification has 3,000 plus pages. And then if you look, it also has a ton of specifications for profiles and services. And you have different types of operation, mesh, and you have sort of regular advertising and then the authenticated communication. How do you start with Bluetooth Low Energy if you want to do this and do cool things like this?
It's a good question. I think if you start with Bluetooth, then there are some easy tools, as for example, GetChecker or BeetleJack, which you can start with. And I think most important is that you get used to the protocol. So analyze the communication of devices. So very easy to analyze the communication for Bluetooth protocol is via the host controller interface. This is possible on Linux devices via the Bluetooth monitor. You can also extract the host controller interface Snoop block on Android devices. So this is a developer feature. And the benefit in this case is that since the encryption is established in a link layer, and you capture the devices on the host layers, then they are not encrypted, and you can check what the protocol is doing. Because if you're sniffing the protocol over the air, which is on the one side very complex and not working very well, Then you have encrypted traffic if they're using encryption, and then you cannot determine what is happening there. So the best way is to, I think, is to start to get a device, get the host controller interface logs, put them to Wireshark, and analyze the connection setup and try to find the required parts in the specification. It's not easy, but once you get used to the specification, it also makes kind of sense.
Cool, thank you very much. So we don't really have time for another question, but feel free to reach out to Sarah in the break. I think she will be happy to answer any more questions. Thanks again a lot for the talk, Sarah. And a round of applause. Just 1 second. Great. All right. Hello, everyone again. Welcome to the next talk. My name is Oliver Netting, and I'm introducing to you Ido Cohen and Arnold Osipov. Yes. And they're talking about today how they went and found a suspicious log entry, and in the end, it brought them to a very interesting and sophisticated crypter. And I'm very much looking forward to hearing your talk, and yeah, give a round of applause for the two guys, and good luck.
Thanks, Oliver. Hi, guys. Thanks for attending our session, from simple log to sophisticated crypto. My name is Arnold, as already introduced. I'm here with my friend and colleague, Ido. We both live in Israel and work as malware and threat researchers at the company named Morphisec. And today, we want to share with you our story on discovering the Baba Data crypto And we'll do so by showing you our point of view when we investigated something that might have been simple or irrelevant anomaly in one of our customers' logs. And later on, we'll dive into the crypter's internals and understand how it works and how we use that information in order to uncover a major campaign that targets some NFT communities, including some additional campaigns that targets the Ukrainian entities. But before we start, let me say a couple of words on what the crypter is, for those of you who may not familiar with it. Let's do that with an example. Let's say we have a threat actor that wants to use some open source information stealer for some of his criminal activities. If he'll use it as is, theoretically, security solutions would be easily detecting it either by its strings, metadata, or even some of the code blocks. And that's exactly when cryptors comes in handy. They solve this problem by taking this malware or the information stealer as an input and performing some obfuscation, encryption, and code manipulation. And hopefully the output of the crypter is an undetected file. Without further ado, let our journey begin. So one of our tasks as security researchers is to keep track on current trends and understand the threat landscape and its evolution. And in order to do so, we use classifications to divide the massive amount of data we got from our customers into specific threats or behaviors. And that helps us to cluster the data and follow trends more easily. So one day, while going through one of our customers' logs, we came across an anomaly. Specifically, it was a Crybot, which is an information stealer. And at the time, we had plenty of those infections, but the thing that caught our eye was the fact that the infection chain that led to it was something that we haven't seen before, and the Crybot was being executed from an executable that was being signed by Microsoft, which was legitimate. And at this time, we were taking those first-stage hashes, like every person in our field would do, to VirusTotal. Yeah, and we were surprised to see a 0 detection rate, which means that no security solution was able to identify this file as malicious. And we were even more surprised to see that this was the case for multiple scans in a very long period of time. We took an additional hash from one of our prevention logs, and the result was the same. So at this point, we were extremely curious to understand how the crypter works and what keeps that low detection rate. So in order to do so, we needed to get our hands dirty and dive into the crypter's internals. So this is an example of how the infection chain looks. And you can see that it's composed from several components, and we'll explain each and every one of them. Let's start with the installer, first stager. And the installer starts with decompressing its files into a newly allocated folder on the disk. And this is how this folder looks. And you can see that among, it has very files in that folder. And among them, most of them actually, are in fact legitimate. They belong to a legitimate application or some open source application. And the ones that marked in red belongs to the malicious infection chain. Once the installer finishes its execution, it calls the file marked as 1, the executable. And this executable's sole purpose is to invoke the export function of the next stage malicious DLL. And as you can see, it does so with just a few lines of code that are placed at the very end of a log function, whereas the rest of the code in that function is actually benign, again, belongs to a legitimate application. Once this DLL is being invoked, it starts its execution by calling some additional DLLs, and this part in the crypter is written in a modular way that helps the crypter's users to choose which functionality they want to use. For example, the functionalities that we've seen are, for example, a DLL that performs persistency in some various different ways, and a DLL that can download additional malware, and many more. So once the DLL finishes calling those modules, it will load a file from that folder to memory. In this example, it's an XML file, but we've seen many other file formats, such as PDF, PNG, and many more. And this file is structured as the follows. In between its legitimate XML strings, we have the first shellcode. Later on, we have a configuration structure. And after that, we have several of encrypted chunks. And once the main DLL reads and loads that file, it will invoke the first shellcode by holding a hard-coded offset to it. This shellcode has several functionalities. One of them is to load the configuration structure that was placed in that XML. And this configuration structure holds the decryption key, and the decryption key for those encrypted chunks, and their offset and size on that file. And those configurations, those encrypted chunks are actually the final payload and the second stage shellcode. And after loading the configuration structure, it will decrypt those chunks and concatenating them to their original form. Then the decryption shellcode will invoke the second stage shellcode, which is the injection shellcode. And this injection shellcode, well, is responsible for injecting the payload to the original process memory. And that's the high-level overview on the infection chain. But for those of you who want in-depth information on that crypter, can check our blog for more information. So why did we name it Baba Deda? The following is a code snippet from one of the shellcodes, specifically the second one, the injection shellcode. And if you take a closer look, you will see that there are two D words in there. The one in green, dead beef with a typo, which is known to be used as a magic debug value. And the second one in red, Baba Deda, is in Russian stands for grandma, grandpa. So it was an easy choice, as there were no any other indicators to choose from. Moving on to what makes it so evasive. Well, if you remember, we have the code logic that is split into several DLLs, and those DLLs are placed among many other legitimate files. And the code in those DLLs are placed again among many legitimate code. And on top of that, in newer variants, we've seen that the main DLL is being loaded by a newer technique that called the Dll Side Loading, which helps reducing the amount of malicious files on that folder by one and results in executing the final payload from a legitimate process, as if you remember, we've seen in our prevention log earlier. And in addition, we have the final payload and the second stage shellcode encrypted in some file format, for example, the XML, and they are encrypted, as I said, and splitted. So at this point, we have the couple of logs. From there, we extracted some hashes and understand how the crypter works. And I'll let Dll continue from here. Go on.
Thank you, Arnold. So after understanding how the crypter works, we had to figure out what are our next steps. I like to look at analysis and research as two different things. In my point of view, analysis is focused on a specific piece of malware or a specific task, such as incident response. On the other hand, research is a broad field which is redirected as new information are revealed. That's actually exactly what happened in our research. We started by looking at the Baba Data crypto itself, and now we are moving on to find its usages in the wild. At this point, we have a pretty good understanding about the inner workings of the crypto. We can use this knowledge to translate it into a Yara rule. For those of you who don't know what a Yara rule is, all you need to know for now is that Yara provides you a convenient and intelligent way to search for byte strings, for bytes and for strings and byte sequences in binaries. So our Yara is composed of 3 main indicators. The first 2 are being the Baba Data and dead beef placeholders Arnold just talked about. And the third one are a few bytes from the decryption shellcode, which I remind you is not encrypted on disk. Once we have our Yara rule tested and ready, we can use it to hunt for more samples. We hunt in our own data, our own telemetry from our own customers, as well as online malware databases such as VirusTotal and Malware Bazaar. Those databases usually let you use your own Yara rule in order to find for match samples. So after running this sample collection, we had a pretty large database of Baba Data samples that we needed to extract some information from them. So we wrote an automation that extracted some IOCs, which I'll talk more in a bit, about them in a bit. And then we used open source intelligence to find some references of usage in the wild. So let's go back to the automation and understand what data we need to extract from each sample. To do that, we need to understand what is our goal. And our goal was to find usages in the wild. So we figured out that the sample source, network activity, and the final payload classification will be enough for us. And as you can see, there is an example. This is an example of our automation's output. The left column is the final payload, and the right column is the corresponding network activity, network indicator, which can be your full URL, domain, or IP, or even blank if we haven't succeeded. We used this output to see what malware families made the most use of the Baba Data crypto. So this one was pretty interesting to see. Then after collecting, extracting all of the data, we started open source intelligence. We used online sandboxes, malware databases, social networks, and of course, Google and VirusTotal to see any correlation between what we found so far. And that's when we came across the following tweet that matched with one of our samples hashes. The interesting part in this tweet is that it provided us an additional information to work with. As you can see, there is some kind of app called Moonbeam with what's supposed to be its domain, but actually it's slightly different from the original one. And a Discord message, sorry, it's small in here, the Discord message that classified as a scam alert. We wanted to see if there are any other services that follow the same pattern. So we took the IP address of the fake domain, and we saw that there are indeed other services listed under it. The most famous one you might be familiar with is a fake domain of Larva Labs. And then we got inside those fake website, looked inside the code, and we were able to find some watermarking that allowed us to write a crawler which will find additional fake websites like those. And after running our automation, we found a bunch of them with one specific common ground that they are all some kind related to the NFT and crypto communities. The last piece of information we wanted to verify is whether the Discord message is consistent among all of those services. So we entered the Discord server, the official Discord server of each one of them, and we found that indeed they are all having the same Discord scam message. At this point, we understood that there is some kind of an ongoing campaign that targets the NFT and crypto communities, and we decided to dig deeper, and that's what we found. For those of you who don't know, the NFT and crypto communities are highly dependent on Discord as the main communication channel. The attacker knew that fact and used it in order to find new victims. Once he targeted a service, it will add its bots into the Discord server of this service, and those bots will send a direct message to each member of the channel. As you can see, the Discord message has an official looking of username and title. The Discord, the message body calls the victim to download the new desktop app in order to gain access to the latest features. And at the end, it provides a link to the official website, which is different from the official one. For example, in this case, debunk, the official website is debunk.com, where the provided one is debunk.found. Once the victim falls into the scam message and clicks the link, it will be displayed with a website that looks almost identical, with one main difference, that the login button is now a download button. Yeah. If the victim continues and downloads this file, it's actually a malware that, upon execution, provides the attacker a full control on the infected system. We decided to publish a second blog post that details about this threat actor and the attack chain, which you can go and read about. Wait. We actually tracked back the activity of this attacker, and we found that it was active since November 2020. And the more interesting part is that since August 2021, its preferred crypto is no other than the BabaDeda crypto we just talked about. So that actually explains how we got to this campaign at the first place. We wanted to see some usages in the wild, and we got them. At this point, you may ask yourself, why do we publish our work? Why do security companies and security researchers maintain an active blog? There are actually many answers to this question, but for us is to hopefully make an impact, I think. This figure shows how many new targeted services were each month by this attack chain and threat actor. And as you can see, before releasing our first blog about the BabaDeda, there were around 15 new targeted services. And our first blog only briefly discussed about this ongoing campaign. So the impact was, of course, close to none. And then we decided to publish a second blog post focusing on the threat actor, its evolution over time, its infrastructure, and much more. And finally, we got some impact. And as of today, we can say that there are no new targeted services. We can't say for sure we caused it, but for our own motivation, we do like to think so. Okay. Another reason for us to publish our work is to help others with their research. For example, let's take the case of BabaDeda against Ukraine. The Ukraine CERT has published that the Ukrainian state organization has been targeted to SaintBot and Outsteal malware attacks. In this blog post, they provided some details, not many, and with some IOCs, but didn't explain so much about the infection chain. Then security company named Telsi took the work and expanded it, and what they found is that BabaDeda was used to drop the Outsteal malware. You can go and read more about this. I'm encouraging you. Very good stuff. So let's take a recap of what we talked about today and what are the main key takeaways we want you to take from this talk. We'll begin by understanding the threat landscape you're working with. If you recall, that's how the whole research story began at the first place. We knew how certain malware infection chain would look like, and that helped us to spot the anomaly between the rest of the logs. Look at the bigger picture. Although we started by inspecting the Baba data crypter and its inner working, we then immediately took a step back to understand what role it plays in a full infection chain in a real life scenario. Use automation to make your analysis easier. When you are dealing with a large amount of data, you must automate as many tasks as possible to make your analysis and research much easier and quicker. For example, in our case, we have automated the sample collection, the IOC extraction, the crawler, and many more components. And finally, share your findings and make use of other findings. This is a great community, contribute to it. It will help others in their work and hopefully will help you in your future work. Thank you, everybody.
Cool, great guys. Thank you very much for the interesting talk. It was nice to be taken on your journey of discovery, and also, I mean, linking to the keynote from this morning, sharing your findings, sharing what you figured out. It's a really cool thing to help the community. And maybe some of you got interested in also doing similar stuff. So yeah, we have time for some questions. So when you have questions, feel free, come to the microphone.
Between the two blog posts, there seem to be around 4 months, more or less. How much human efforts there is behind this kind of research, and how many people were involved, and was this, let's say, a focused effort on that, or how was this done, let's say?
So actually, after posting, as I already said, at the first blog post, we briefly discussed about the campaign. So we already knew that there is some kind of an ongoing campaign. What we didn't went in much details and understand it fully. But we keep our eyes on it, and then after a certain period of time, we decided to go back together. We worked together not only because it was is a lot of work to be done, but also because it's fun to work together. And we got back and we decided to investigate more this threat actor. And it was, I think, at the same scale of the first research, but it's different because the first research is more about reverse engineering and malware analysis, where the second is more threat intelligence and those sort of stuff. But yeah.
Thank you.
Thank you.
You had this slide with the bullet points about what made this scripture so evasive. I'm new to malware analysis, but still none of those bullets was really new to me. So is there any really specific thing that made it so evasive, or is it actually not that hard to make a crypter with a 0 detection rate? So is it common? Is it a common thing, or is it really that special?
So first of all, it's not that hard to make a crypter so evasive, but the thing that was special here was the fact that this crypter was evasive for a very long time. That was what interesting in this part, and it does that by combining all of those bullets, as you said, together. That's how it does that.
Very nice. Then, yeah, thanks again, you guys, for also making the trip from Tel Aviv here to Munich to present. And thanks a lot. Another round of applause. And here's also a small speaker present.
Already took one.
Okay, yeah, there's still people coming in, but I think looking at the time, we should get started. So please take a seat, and yeah. It seems the other talk took a bit longer. Yeah? So, all right, then let's get started. So, welcome again to the third talk in this block before the lunch break. My name is Oliver, I'm the MC for the session, and I want to introduce today to you Christian Bauer. He's talking about building a security program for SaaS product development. And I think the gist is how to get security right in a new product development. So he will hopefully show you how to do that. So thank you very much for coming by and sharing your talk, Christian, and give an applause and have a nice talk.
Well, thank you for the introduction. So as the name implies here, this is basically going to be about how to secure cloud-based product development. But before we start, maybe a few words about myself. So I've been working in the software industry for a few years now. I started out as a software engineer originally, but then transitioned over into a security role. And I'm currently working also as a security engineer, securing an as-a-service platform, which is currently running on 2 cloud-based platforms. And this talk is a kind of a summary of the things I've learned over the years, both in my current job, but also in my previous job, where I've seen quite a lot of different cloud-based products. Okay, so imagine you're a security engineer and you're starting a new job right today. You're working for the startup called ACME, and they've hired you specifically to build up their cloud security program. That means you're the first person who really thinks about security from a holistic perspective, and hopefully knows what you're supposed or what they are supposed to be doing. And when we're talking about product, their product is what you see very often these days. On the one hand, it's an as-a-service offering, can be platform as a service or software as a service. It's running on those usually well-known cloud provider platforms. And their technology stack is also something you see very often these days. So the applications are packaged into containers. The containers are being deployed and executed by Kubernetes, and you have some additional cloud service around it that you need for compute instances, for storage services, and so on. So this is not a thing, let's say, unusual that you can see in cloud space these days. So the question is, where do you start, right? Security is a huge topic, and you can't do everything on day one. You have to somehow prioritize and think about what can you do at the beginning and what can you do later. That means at the beginning, we want to go for some easy wins, right? Things which are so-called low-hanging fruits, but at the same time have a high security impact in terms of improving the security posture of the product. So how can we do that? And that's basically what this talk is about. How can we define a security roadmap that somehow starts in a relatively easy way and then scales up over time? So security activities that I'm going to present on the next slide are grouped into different phases. Phase one is like the absolute basics that really everyone should start with. And then starting from phase two, we're going to have more topics that might only pay off in the medium term. Whether something should be in phase 2 or 3 or 4 is a little bit, let's say, it's always biased. It depends on what's your background, right? For people here who have a web application security background, they might complain, hey, there should be more web application security in there. I've done a lot of work on the infrastructure space, so obviously it's maybe a little bit more biased towards infrastructure. It also depends what's the current security posture of a company, and so on. So long story short, while phase 1 should really apply to everyone, afterwards it depends what's the best approach for you, but it's more like to give you some inspiration. All right, so what are the security phases? I've defined 4 phases, and if you do all of those, you already have achieved a quite good security posture. Doesn't mean you are completed, but you have, I think, some good achievements. Phase 1 at the very top, as I say the basics, I'm going to talk about those in detail. Phase 2, these are already some additional topics. I will briefly cover them, and unfortunately, regarding phase 3 and 4, I don't have enough time today to talk about that, but I have backup slides if anyone should be interested. The idea is, phase 1, I said the basics. Phase 2 is some topics that are, again, easy wins, but at the same time should pay off on the medium term. Starting from phase 3, we have some topics that are really either need a lot of effort or are only going to pay off on the long term, especially for phase 4. So I say that I don't have much time, so let's get started. Phase 1, and this is actually the very first task that you have to do at the beginning. So remember, you are coming in, it's your first day, and you have no idea what you're dealing with. You don't know how to secure something if you don't know what you have. So the first idea is you have to get an overview of a cloud environment. Which cloud providers are you using? How many accounts do you have? Do you have a segregation between production and non-production environments? And most importantly, you need access to those accounts and start looking into them. What kind of infrastructure is deployed in those accounts? What kind of services are being used? And most importantly, how are those services configured from a security perspective? We'll talk about that a little bit later. If you're only dealing with a handful of accounts, so in AWS calls it accounts, on Google Cloud it's called projects, but it's basically always a cloud environment. You will easily run into the scalability problem. If you have to deal with dozens or maybe even hundreds of accounts, you can't go over them manually, right? Cannot click log in into every individual account, start clicking right on the dashboard. That's not going to scale. So you need some form of automation. And there's a lot of tools out there that can really help you with that. And these are all open source tools that I've listed here. And that list is not even complete. Which tool is the best one for you depends on what you prefer working with, and also how many cloud platforms you have to cover. Some are multi-cloud, some are only supporting one individual cloud firm, in particular AWS, because it's the most widely used one. It also depends how you want to handle the tool and what kind of output. Are you fine with reading JSON output, or do you need some tabular output? Do you want to process this further? Either way, I personally have used TeamWeb a lot because it's super flexible and supports a lot of different platforms, including software as a service platforms like Cloudflare or GitHub. But it is, you can use that to automatically obtain data from your environments and specifically kind of select what kind of information you are looking for, what kind of misconfigurations maybe. And that gives you a basic idea on how serious security was taken in the beginning, right? If you already see some bad things there, you know, oh, this is not a good start. Otherwise, if it's looking roughly good, you know, okay, I don't have to start from the beginning. Either way, so I've used this tool to collect a lot of information, and then I have to start looking for this information. And the very first thing that I usually want to do there, that's step 2 now, parameter protection. And in the cloud, we have 2 parameters. The first parameter is identity and access management. And I think this is a big differentiator of cloud compared to on-premise systems. Because the cloud provider API is the thing that's used to access your cloud environments. And that's reachable over the internet to everyone. The only thing that keeps you from getting breached on the cloud provider level is to keep your credentials secure. That's why it's so important to really look at what kind of credentials are currently being used. So we have to differentiate here between human users and service accounts. Human user, we know you have a form or a login form, you log in with a password maybe, then you get in. That's what, at least on AWS, is supported actually. You have console login with a password, or if you need API, programmatic access, you have an access key. Both are long-term credentials that do not expire and you don't have to rotate them, which means that's a problem. And actually, if you look into the publicly known security incidents of AWS customers, very often the initial access vector for the attacker was a leaked access key, like somebody committing it to a public GitHub repo. So you have to somehow get rid of those access keys, or more generally, long-term secrets. So for humans, there's no need to use it anymore because you can set up single sign-on. The idea is you use single sign-on, and then the human user can obtain a short-lived token to access the cloud provider interfaces, including the API. And as we're talking about single sign-on, we should obviously be using multi-factor authentication as well these days. And particularly for the production environment, I think it's worth investing in the physical authentication tokens as well, like free to do, which I think are very cost efficient. Now, single sign-on is not going to work with service accounts, right? We need something else there. I see quite often that you have an application that's running on, for example, Google Cloud, and needs access to the Google Cloud API. That means your application is going to need a credential. People sometimes use those long-term secrets just for that. But you don't have to do that anymore, because the better way is to obtain a short-lived token from a cloud provider metadata service. So in the case of, for example, AWS, if you're running applications inside Kubernetes, they have a feature called IAM roles for service accounts, which means you sign a role to your application. That means the application can get a short-lived token from the cloud provider metadata service. There's no long-term secret involved anymore. And those tokens usually only have a lifetime order of magnitudes of hours. It's the same on Google Cloud. The feature there, if you're using their managed Kubernetes service, is workload identity, which works basically the same. You have an application running inside Google's managed Kubernetes, you assign a role to it, and then you can obtain a short-lived token from a metadata service. So that works very well if your application needs access to the cloud provider API of the same platform. Things are a little bit more complicated for cross-cloud provider access. Like application running Google Cloud needs access to AWS API, or the other way around. Until maybe 2 years ago, the only solution was you generate an access key in AWS, you export it and basically import it into your application on Google Cloud, which means you have a long-term secret that you can leak again. Luckily, you don't have to use that anymore because you can now use identity federation for service accounts. So if I continue this example, my application running Google Cloud obtains the token from Google Cloud as described here. Then this application starts calling over to AWS and authenticates with the Google Cloud token, which is accepted by AWS, and they will issue an Amazon token for that. Now my application can use that Amazon token to access the API. And all of those tokens are again short-lived. And this works because on the AWS side, I will set up saying, hey, if somebody shows up with a Google token that was issued by Google and is assigned to a particular identity at Google, then this person can now get an AWS token. Meaning that I've completely eliminated the need for long-term secrets on both AWS and GCP. On the same works with other cloud platforms as well, which means I've reduced already the risk of leaking long-term keys, which is often a problem for many people or companies. So that was about access keys or credentials. Another issue I see very often at the beginning, people, you have to sign IAM privileges, right? You have a token, that's one thing, but you also need to define what can I actually access with the token. And people often then do assign a lot of privileges, right? Because it makes life easier for them. So it makes a lot of sense to look over all those IAM policies and basically see if you find these kind of situations where people use wildcards, that means can do anything, to cut them down. So this is basically least privilege principle that you have to review. There was the IAM parameter. The second parameter, that's basically the same that we have in classical non-cloud on-premise networks, which is the network parameter. So what I have to look for is do people actually have a network architecture, meaning public DMZ and private zones, where most stuff should be deployed in the private zones, and only the bare minimum should be in the public zone with public IPs reachable to anyone. And the second thing is firewall reviews. That happens really often, that people start opening up ports to the internet. Internet means, again, to anyone. And you have to look in particular for things like open SSH ports. Usually, when you open up an SSH port to the internet, it takes only a few hours and people will start brute forcing you. And then if you have a password like CentOS, then you will be breached. Now, what I've said is we're going to basically look at the output from the tool and go over it manually, right? So today, everything might look fine. Maybe next week, it's not fine anymore because somebody has already started opening up firewall rules or generated access keys. So we cannot manually go over that every single day or even once a week because that's not going to scale again. So we need some way of automatically monitoring our entire environment for this kind of security violations. And the solution to that is called Cloud Security Posture Management, which basically is just a piece of software that's going to look into your cloud environments by calling the APIs and checking if anything violates your predefined security policies, like what I've said before, right? Either you have access keys there, somebody has opened up the firewall rules, somebody has a storage system that is publicly reachable to anyone. And there's different solutions for that, how you can implement it. Option one is cloud provider service. They have, everyone supports that, basically has a solution for that. There are also third-party offerings for that. For example, software as a service platforms. Basically, you grant them read access to your cloud environment and they can monitor everything and then tell you or raise alerts if something goes wrong. Some also offer the tool itself, so you just get a software package and you deploy and operate it inside your own environment. There's the advantage that you still have full control and don't have to grant access to a third party to your environment. Or third option, open source tools that you can use to build basically your own cloud security posture management. Cloud Custodian has been around for many years. I think it was one of the first tools, and it's very popular, I think, with some people. Steampipe that I mentioned in the beginning for inventory, you can also use that for cloud security posture management. Although at some point, depending how large your environment is, you might run into scalability problems. But the idea is this allows us to monitor everything automatically. And once a violation is detected, you get an alert. And you can run this maybe, depending on the solution, in almost real time or like once a day or once a week. So next part, sooner or later you're going to have a security incident. But it's minor or major is a different story, but when you have that happen, you have to start investigating. And investigating means you have to go over your log files, right? Because without that, you cannot really do a proper investigation. What I found is the easiest way to do that, to set up a central log data sink and to just dump all your log data in there, just for storage at the beginning. And the most cost-efficient solution for that is to use one of the storage services like Amazon S3 and so on. Because it's easy to set them up. You can drop as much data in there as you want because there's kind of no limit, and they're very cost-efficient as well. You can use a SIEM, but that can become very expensive depending on what kind of solution you are using because of the huge amount of data that you're dropping in there. And the first kind of log data that we feed in there is going to be the cloud provider logs. If you have a breach on the cloud provider level, that means the attacker is going to call the cloud provider APIs. And those calls are going to show up in the management API logs. That's why it's important that you activate forwarding these API logs into your central log data sink. You make sure nobody can mess around with that, so you need access control on that. Now we are just storing data, right? At some point, when you have a security incident, you might have to query this data. And depending on how large your environment is, we're talking here about querying gigabytes of data. 10 gigabytes, maybe even 100 gigabytes. So you're going to need some infrastructure for that. But as I said in the beginning, our scenario is you're the first and only security engineer. You don't have the time to maintain and operate infrastructure for that. So my recommendation is here to go serverless. You have these services, that data lake querying services like Athena or BigQuery. The same should exist for Azure, that allow you that. They're very easy to set up. They don't need any maintenance at all, and you can query them also in a relatively cost-efficient way over your entire data. Basically, the more data you query, the more you have to pay. But if you don't query that often, it makes sense to do that. And it's not a lot of effort to set up. Right, then incident response, as I said, when the incident happens, you need to be prepared. And it's a good idea to do that in advance, right? How does your basic process look like? You need to store evidence somewhere, so you need a dedicated location for that.
Makes sense to track your incidents in the issue tracking system, and you need to find in advance who's your contact person for what topic, right? Operations, you have to talk to them. If customer data is affected, you have to reach out to your customers, but you're not going to do it yourself. You need someone from customer support for that. So that's important to define who's your contact for what topic in the beginning before something happens, so that by the time you have the incident, you're ready to go. And finally, vulnerability management. I think that's a very old topic. It's not too different in cloud. The only difference is we have vulnerability management on 2 levels. We have to scan for vulnerabilities first on the container level, which also includes our application dependencies, and on the host level, meaning the host machines where our containers are being executed. There are open source solutions available for that. Anchor and Claire working very well. They work primarily for containers. Host machines is a somewhat more complicated story. I don't know any reliably available solution for that on the open source space for vulnerability scanning on the host machines. And one more thing, CI/CD-based scanning makes a lot of sense, yes, but it's not sufficient, right? If I build a container image today, I scan it today, and it has no vulnerabilities, this assessment might not longer be true next week. So I need continuous vulnerability scanning. That's something some people forget about that. And identifying vulnerabilities is one thing, fixing them is another story. We have to write down SLAs for that with engineering and agree on something like 1 week to get a critical or high vulnerability fixed or something like that. Well, and that's already phase 1. This should give you a base standing. That will take you at least weeks, maybe a few months, depending on how much in-company support you will get for that. After that, we'll continue with phase 2. And then the first thing is defining the security baseline. As a security engineer, you usually know what you should do, right? But that's usually not clear to engineering. So it's very important to write it down, define what are your expectations towards engineering for that. And you don't have to come up with this yourself. There's a lot of good stuff out there, in particular the CIS benchmarks. They have basically security best practice not only for cloud providers, but also for Kubernetes, for Docker images, and so on. It makes sense to just adopt those standards. Once I've written down my baseline, I need to set up the monitoring for that, right? To see if people are actually following my security baseline. And this is where I can use the cloud security posture management, because I have to implement my baseline basically in there to look for violations of my baseline. Then another easy win, Kubernetes or container deployments. A lot of people, when they run the application inside containers, those applications are running as root. I've seen this so often, I think I don't know what's going on there, but nobody's thinking about it. There's a very easy way to override that. In Kubernetes, you have a so-called security context object. And there you have a parameter called run as user that allows you to override that. You just specify in your deployment, no, run this as a non-privileged user, and then it's no longer running as root. This is super easy to implement. And there's a lot more security features in Kubernetes that you can use. Finally, or something that people sometimes miss, if you have 2 applications running in the same Kubernetes cluster, there is no network isolation between those applications. Application A can always reach application B and vice versa. That's just the way vanilla Kubernetes works. The way to fix that is to use so-called Kubernetes network policies, which are usually never enabled by default. You have to explicitly enable them and start deploying network policies, which means basically it's a firewall rule that applies inside the Kubernetes cluster. Then again, as I said about using this run as user option, how can you be sure that people are actually using that? You have to, again, set up the monitoring for that. That means you have to extend your cloud security posture management to also monitor your Kubernetes clusters to see what people are deploying there actually and how. A very different topic. So security in cloud usually means you have a scalability problem. That means you need to automate as much as possible. For that, you're usually going to need some tool, right? So for example, I want to run a dynamic application security testing once a week. I want to run some board scans maybe every day. Same with credential scanning maybe. So I need some platform that allows me to define what tool am I using, how I'm calling this tool, how I'm going to process the output, and where do I push this output. Then I need a time schedule for that. This is what workflow orchestration engines are very useful for. Again, there are cloud provider services, serverless, that allow you to do that. There's also 2 Kubernetes frameworks for that, which is Argo and Tecton. I personally used a lot of Argo workflows, but functionally it's almost the same as Tecton, so it doesn't really make a difference. Or if you don't have that much security automation, of course, you can just spin up a virtual machine with a cron job on it that schedules everything. a lot of this is reactive, right? It's how do we get things in a more proactive mode? This is not even cloud specific. I have to hook into the software development lifecycle. That means I need to be involved in the design phase. Otherwise, I will always keep running after people to get things done. And yeah, the pen test, kind of obvious, I think. Right, and that's phase 2. And then in theory, I can continue with phase 3 and 4, depending on what I want to do and so on, and how the security posture is now. Now, before wrapping up, some final thoughts. So our startup SME is dealing with business customers. And there are some customers that will say, I really like your service offering, but I will only do business with you if you have a security certification, like ISO 27000 or SOC 2, something like that. Now, I'm not going to get in topic if those certifications are going to improve your security posture, but I think that's the wrong way of looking at it. You can use those programs to actually push for your security again, or to get things done. Because if somebody asks you, hey, why do we have to do this? You say, well, we need this for SOC 2, and if we don't have SOC 2, we will not win that customer. So that will help you a lot, because nobody's going to argue about bringing in more revenue, right? So you've changed security of now being a business enabler, which is making discussions a little bit easier in my experience. Yeah, and finally, that's more a culture question. How are you approaching security, right? Security is a very cross-functional role. We have to deal with a lot of people, right? You talk to customer support for incidents, and as we are talking about product security, we are dealing a lot with engineering. You have to build a relationship with them, and that means, are you going to be a guy who's just going to make trouble for them and is going to blocking them all the time? Or are you more seen as a valuable support function? Because this can really influence a lot on how whether they are willing to work with you or not. Right, and before I wrap up, I'm not the first person to think about how to do this in a structured way. There's a lot of very interesting material out there in terms of talks and also documents. I highly recommend going through this if you are interested in this topic. Well, and that's it.
Cool. Thank you very much, Christian, for the interesting talk. I think the one key takeaway is that as a security person, you should not try to be the blocker, but more like a valuable resource. That's a very good recommendation, I think. Are there any questions from the audience? Please step forward and shoot out.
Hi, thank you, great talk. I was wondering, what is a good way to get more support by the engineering team and everybody in the company for getting a better security system?
It's a tough question. Well, I think there was one of a slide that I've removed for time reasons. I think you need management support. If management doesn't care about security, then things are going to be difficult. And the other thing, I think, if you work with different teams, there are also people who are for security and some people who don't care. It's important to identify basically those people who are interested in security, because those are going to be your allies. And I think these are basically kind of security champions that they can try to push.
Thank you.
Hey, a question about the last thing you touched on security culture. Yeah, they building relationships with other departments and not being a blocker. Sounds great until you hear that someone is trying to put an RDP password logon machine on a public IPv4 address. So where's you have the one side where everybody here at least thinks they have to put the foot down, but then you kind of go against that. How do you keep balance?
Yeah, so there's an interesting talk from Netflix, and their security culture says trust but verify. Their idea is they have the monitoring in place. If one team screws up, the monitoring will show it up immediately, and then they go to those people and tell them, hey people, you have to fix this. And they have dashboards that show how well teams are doing. They're kind of playing the teams against each other, saying, oh, this team is really doing well. You're more like down there. Maybe you should really do something. This is kind of an intrinsic motivation for other teams. That works for Netflix. I don't know if that works in other places too.
All right, thanks.
So actually regarding working with our departments from my experience, it helps. So this also notes to others when you accept that they have problems or issues. When you take them serious, from my perspective, they take also serious if you see that you're competent. Most of the time, what developers and engineers think, okay, someone comes around and he wants something, but we have other problems. So that's just a remark. I have 2 questions. First, you talked about setting up a parameter. There's nowadays this thing called zero trust model, and there are a lot of guys that are saying, oh, everything has to be secure with zero trust. What do you think about that one? Would be my first question.
Yeah. So, I mean, it's a buzzword, right? Zero trust. I mean, I'd say.
The thing is, with the parameter, you kinda. So if you had said in a later phase, you remove the parameter and do everything, for example, in a VPN or separate control and data plane, then I would say, okay, for the first step, parameters are good. But in my experience, especially still in cloud, people are doing, oh, I'm in the trusted parameter, so that's no problem anymore.
Right. Well, I mean, I think it's not going to. I'm not going to say this will zero trust will remove the network parameter. You still have it, right? As said in Kubernetes, inside this idea, you are inside a trusted island, then everything is good. I think zero trust for me is the opposite. It means microsegmentation. And microsegmentation for me includes network parameter, maybe on a smaller level, but still it's there. And I think the IAM is actually in the cloud is very easy to do zero trust for human users. You can say you can set up IAM policies that say you're allowed to log in, but only Monday to Friday and only from a particular IP address range, for example. I think in cloud is maybe the easiest place to implement zero trust.
Yeah. The second question, I was a little bit surprised that you did not talk when talking to the developers about the supply chain stuff, because especially I'm more of an infrastructure guy myself, but the thing is, with the packager situation today nowadays, I would say, okay, we have to really look where the developers they're getting their software from and their libraries. So, in which phase would you say is that? Later on?
It depends.
Okay.
So, well, I mean, if you had problems already in this direction, you pull this into phase 3 at least, obviously, right? I mean, vulnerability management is covering this a little bit, but not completely, obviously. But I'd say I probably put it into phase 4.
Okay. Cool, thanks.
Over time a bit already. Is it a quick one or?
Yeah, maybe I can do a quick
cool.
one. Thanks again for the presentation. So I'm wondering, so here you're starting with the assumption that you have a full access into the network, to the system, visibility. How much would it be different if you have a partial or a non-view? You know, if some part is outsourced or you're part of the team that is actually doesn't have access to the entire system?
Well, if you have no view, you have a problem, right? I mean, you can still do the parameter, right? Scan that, but that's it. If you have a partial view, it depends. I think a lot. What do you have access to? Like, do you have still access to cloud provider API, and that's it? Or do you also have access into host machines or things like that? I think you should always go for access as a security team, because actually most cloud providers will give you a dedicated security read-only role just for that purpose. It's called security auditor role. And you should always go for that. I think if you don't have that, then you can't do work. I mean, it's impossible.
Cool, great stuff. Thank you very much, Christian. Thanks to the audience for the good questions. Another round of applause. So now we have lunch. Enjoy lunch, and there's also soft drinks in the fridge now. If they're empty, please approach the people from Hilton, from staff, and enjoy.
Just so you know, people can hear you on the internet and such. Be decent.
Okay, everybody. Welcome back from the break. Please take your seats. We're going to start in a couple of seconds. So, talk after the break. Let me welcome Dimitris Prazakis for his talk, Attacking Malware with AI. Have fun.
Thank you. Thank you. I have a mic. Thank you. Hello, everybody, and welcome. I hope that you have enjoyed your lunch break and that you're having an interesting and educational day so far. I'm really glad and delighted to be here with you today at BSides in Munich, where we're going to have the chance to explore one of the places where the finest concepts of data science and cybersecurity meet. Before doing so, I would like to really quickly introduce myself to you. My name is Dimitris Prazakis, and I'm currently pursuing my master's in cybersecurity at Georgia Institute of Technology, Georgia Tech, in the US. I'm also working as a security engineer at Trade Republic in Berlin, where I specialize in cloud security and infrastructure security. My interests also lie in AI and privacy, and especially where all these worlds intersect with each other. And one of those intersections is what we're going to see here today together. Our agenda is made out of 4 parts. The first 2 of them are introductory. We're going to talk about malware analysis and about sandboxes. And we are also going to talk about machine learning and introduce the tasks of classification and clustering. The third part of the talk is the heart of the talk, Mirage Framework. It's a malware analysis framework with AI, and we're going to explain how it works step by step. And we're also going to have a short session for questions and discussion. So without further ado, let's start. And let's talk about malware analysis. In cybersecurity, there is a job title, malware analysts. And these people, their day-to-day job is to analyze malware. And they do this with the help of certain tools called sandboxes. A sandbox, in short, is an isolated environment in the context that everything that happens in the sandbox can't escape it. If we execute a program in that sandbox, it can't infect the host, right? So that's the first thing it does. And the second thing it does is that it has the ability to study and monitor the behavior of what is being executed inside of it. So in short, it takes a binary, a malware binary, as an input, it executes it, studies it, and then produces a text report. And this report will contain things like network requests made or metadata about the malware. But today, we care in particular about commands this malware tried to execute. And we're going to talk about Windows malware specifically and Windows API calls. Apart from sandboxes, the second introductory point is the task of classification. Classification is a machine learning concept. It's the task of taking an observation, something about we don't know the category it belongs to, right? And putting it into some pre-known category, into some class to be more formal. So let's say that we download an executable from the internet, right? The task of classifying this executable to benign or malicious, to good or bad, is called classification. And in machine learning, we classify objects with the help of classification machine learning algorithms. And one of the most known ones is KNN, K-nearest neighbors, and it operates based on the folks saying, show me your friends, and I'm going to tell you who you are. Or, in other words, show me your nearest neighbors in the vector space, and based on their class, I'm going to predict your category. And we see here the example where this observation up there gets classified as a benign program because the nearest neighbors are benign. Apart from classification, we have other tasks in machine learning, and one of them is clustering. And unlike classification, which is a supervised kind of learning because we feed our algorithms with labeled data, so we feed the algorithm with data that have labels, clustering is a kind of unsupervised learning. We feed our algorithm with unlabeled data, and the clustering algorithm tries to create groups of those unlabeled data, clusters, which we are going to equate today with the concept of classes. Let's see how all these 3 concepts, sandboxes, classification, and clustering, bond together under a framework for malware analysis called Mirage. But before doing so, I would like to talk about a very interesting statistic. every day, almost 500,000 new malicious software and potentially unwanted applications are registered. I would like you to think about the volume. How much volume of malware this is. We need to understand this malware. We need to study it so that we can attack it, right, before it attacks us. We can't do that manually. We don't have enough manpower. We don't have enough bandwidth, right? Malware analysis is a very energy-consuming process, and it takes time. There is, therefore, an imperative need to automate this process as much as possible. Excuse me. And this is where Mirage Framework comes into play. Mirage Framework is an open-source framework for malware analysis with machine learning. And it is used to do mainly two things. To discover new clusters of malware, in other words, to take all these 500,000 malicious software every day and try to group them into clusters that contain malware with identical behavior, and to also classify unknown malware, observations, into clusters that it created. And we're going to see how this happens in a bit. Mirage Framework looks like this, a simplified version of it. We talked about the first concepts, right? So we take our malware binaries, we pass them through a sandbox, produce some text report, and we talked about clustering and classifications. We want to cluster and classify those malware reports. But in essence, clustering and classification are statistical algorithms, right? They don't understand text files. So this is where the second step, embedding of behavior, comes into play. We take those text files and we transpose them into mathematical objects, into vectors, so that we can later classify them and cluster them. There is also a step in the middle, the step of prototype extraction. It's a very beautiful idea, which we are going to talk about in a bit. So without further ado, here, what you see is an XML encoded malware report. And I modified a little bit for the sake of the presentation and for understanding better what's going on. We see three snippets of instructions. The first one is something you're going to see many programs do. The program tries to load the Windows kernel into the process memory, and also it reads the time. Nothing malicious about this snippet of commands, right? But if we scroll a little bit more down, and we study the next snippet, the next sequence of instructions, we're going to notice something at least suspicious. The malware tries to copy itself from the location it is to a Windows protected area called System32. And while doing so, it also renames itself to a Windows well-known process, cs rss.exe. And after doing this, it also modifies the Windows registry keys so that it runs every time Windows start up. So that's not something a benign program would do, right? Why would you copy yourself into a protected area and then put yourself to start up? You may do the latter, but especially those commands in combination show some malicious behavior. And we see another example, another snippet, where the malware just tries to check if it's being debugged. And malicious programs usually do that, excuse me, to understand if they're being analyzed. And in this case, they try to shut down their malicious behavior and conceal themselves. They try to hide themselves from the malware analyst. There is an important observation to be made here from this example, that behavior is often manifested as a sequence of instructions, which we formally call as Q-grams. So a Q-gram is a synonym for a behavioral pattern, let's say. And we saw two examples of 2 grams because they are made out of 2 instructions. And this concept of Q-grams is important because it's what enables us to embed the text files into the vector space. We want to do that, first of all, so that they can be read by the clustering and classification elements, but also because embedding the reports into vectors will enable us to express their behavior in a geometrical way, right? Similar reports, similar malware, are going to be closer in the vector space, and vice versa. We embed the behavior using a mathematical function called embedding function, which looks like this. We're going to explain in an intuitive level what this does. Simply, it gets an input, which is the malware report, a sequence of instructions, right? And produces an output, an n-dimensional binary valued vector, where each dimension represents a Q-gram. It represents a behavior. For example, imagine that we have the three-dimensional space, right? The X dimension, Z dimension, the X dimension, and the Y dimension. We may embed this behavior, this Q-gram, in the Z dimension, excuse me. And say, for example, that the malware tries to copy itself into the Windows protected area, rename itself, and put itself on startup if the value here is 1. Or otherwise, if it's 0, the malware doesn't try to do that. And we may embed this behavior, the malware checking for debugger, on, let's say, the x-axis, right? If it's 1, the malware tries to do that. If it's 0, the malware doesn't try to do that. Imagine this for n dimensions in the n-dimensional space, right? Something really interesting happens when we embed malware in the vector space like that. Because each dimension represents a behavior, right? Similar reports will be close with each other, as we said, and they will form dense clouds into the vector space. If we look at this space from far away, we're going to see clouds, clusters of malware, and each cluster has malware that behave in similar ways. And this exact distribution is what we are going to attack in order to exploit the malware before it does that to us. Before talking about that, however, let's dive into a very interesting topic of computer science, computational complexity. Algorithms take time to be executed, correct? And especially machine learning algorithms scale in a super linear way, let's say in polynomial time, depending on how much data we give them. That means that they are quite slow, and we want to execute this framework every day. So there is an imperative need to reduce the time of the framework as much as possible. There are 3 things that we can do. Either buy more memory and more CPU, but this is limited, right? And by default, we have some physical limits as well. We don't have quantum computers, for example. So that option is out. The second thing we can do is use faster algorithms, but again, machine learning algorithms are refined. Like, they are as good as they may get. We may be able to modify them slightly, depending on the problem, but mostly we can't really reduce how much time they take. The last thing we can do, and that we are going to do, is reduce the data that we feed the framework. So what if, instead of feeding the framework with 500,000 reports every day, we feed the framework with, let's say, compress them with a ratio 1 to 10, and we feed it with 50,000 reports. This is where a very interesting and beautiful idea from 1989, the idea of prototype extraction, comes into play. Instead of analyzing all these initial malware reports, all these data points, what if we could extract representatives? What if we could choose certain data points that would represent all the others? We call these data points prototypes. And luckily enough, there is a prototype extraction, not the optimal one, but a good enough one that runs in linear time. So we take our reports and we try to compress them into a smaller set of reports, which we call prototypes. And instead of feeding our classification and clustering algorithms with the initial reports, we're going to cluster the prototypes themselves and propagate the results of the algorithm back to the initial data points. And here we see the 5 reports, right, that we extracted before, the 5 prototypes, excuse me. And they're being clustered into 3 clusters, one on the top right, one on the bottom left, and one on the top left. One would say it doesn't really make much sense to create a cluster of one person, right, like we do on the top left. Why would we do that? Why would we create a group of 1? And we would agree with whoever claimed that, right? And this is why the algorithm takes a parameter. And we say that if a cluster has less than m members, if our clustering algorithm creates a cluster with less, let's say, than 2 members, we are going to reject this cluster. We are going to put it on the side, and we are going to keep these data points for future reference. Maybe tomorrow, where we are going to have new malware reports, some new prototype is going to be extracted on the top left. And as a result, maybe a new cluster will be formed because it's going to have more than m members. And the same exact idea applies to classification. We draw our decision boundary, and we may say that if a new observation falls here, for example, the closest prototype is this one. As a result, we're going to classify our new observation into this cluster. But if it falls more than dr distance away, let's say here, we reject it, and we keep it for future reference. We described the simplified version of malware. We described how we embed malware into the vector space, how we extract prototypes out of them, and how we can use these prototypes to classify and cluster faster the malware. What we didn't talk about, however, is how we can make this framework recurrent. We said that it's going to be executed every day, let's say, and analyze 500,000 malware, right? This is where a last concept comes into play. The idea of prototype incremental analysis, excuse me. And the framework looks like this. So the first steps are the same. We take the malware binaries, we monitor the behavior, we embed the behavior, and then, instead of classifying the initial data points, we classify the prototypes. On the rejected prototypes from the classification, we run the algorithm of prototype extraction, and we extract prototypes out of them, and then we feed these prototypes into the clustering algorithm. And these new prototypes maybe will create new clusters with the yesterday's prototypes, and so on. What we described basically is this algorithm. This is the heart of malware. This is the entry point, the main function of it. And it invokes all the other three algorithms that we talked about. And this way, our model gets stronger and stronger every day. Our framework can create new clusters of malware, and as a result, it can identify new malware. And in this way, we can attack the malware before it attacks us. The talk is based on a paper called Automatic Analysis of Malware Behavior Using Machine Learning. It's written, I believe, by 2 German professors and 1 Austrian professor about 10 years ago, but it's still relevant. And it's very interesting. If you enjoyed the talk, I urge you to give it a read, because it also has some concepts that we did not have the time to talk about today. I want to thank Sneha for guiding me and helping me prepare for this talk today. Thank you, Sneha. I really appreciate it. And I also want to thank BSidesMunich for giving me the chance to be here with you today and explore one of the places where the finest concepts of data science and malware analysis meet. I would love to connect with you. I have a QR code down here. I hope it works. It's not a malware, I promise. You don't have to believe me, though, right? So you can search me by... Sorry? You can put it into the sandbox. Right. Correct. So, yeah, you can also search me by my name. And I would love to hear your questions and discuss with you about what we presented. Thank you.
Awesome. Thank you very much. Any questions? Just come in front here, please, and ask your questions. Just come in front. Thanks. So we can hear you online as well.
Hello.
Hi.
Hello. First of all, thank you very much for the very impressive introduction of your system. I have just one quick question about it. Where do you get all that information related to the malware from? Because, I mean, it's a huge amount of data you need to put into the system. And do you have any sources, or where do you get them from?
Usually we get those. That's a very nice question, actually. We get those from honeypots, right? Mm-hmm. A honeypot is something like a sandbox. We could say that we expose to the internet, right? And it has some vulnerabilities, and attackers may get access to this honeypot and try to install some malware, but they fail to do it because this is how honeypots work. So we take this malware sample and we throw it into malware. So honeypots usually is the way how we gather those. Apart from that, also self-reported malware from people or things that antivirus has already detected, let's say.
Okay, perfect. Thanks.
Thank you.
Any more questions?
I will suppose it was clear then.
Awesome. Thank you very much. I'm sure you are available for Q&A later on.
Yeah, I would love to talk with you. Thank you very much.
No, I'm going to the other room.
Okay, everybody. So take your seats, please. Wonderful. So the last talk here in the Moonshot track for today, and actually for the whole conference, live from India. Ashika, Ashid, and Manan will talk about how they got into a private code database or code base. And actually, I love war stories, so this is going to be very interesting. And the stage is yours. Have fun.
Thanks, Silvio. So I'll begin. Hi, everyone here. Here we are to present our talk titled How We Got into a Unicorn's Private Code Base Through Analyzing Millions of Mobile Apps. Moving on to the next slide. I'm Ashika. I'm a security research and technical writing intern at CloudSec. Arshit, I believe you're on mute.
Hello. Is it
Yeah,
better?
hi. Yep.
Hello, everyone. My name is Arshit Jain, and I'm working as a full stack engineer at CloudSec. So I love to automate anything and everything related to security. Apart from that, I love to travel and read books.
Hi everyone, I'm Manan and I work as a cybersecurity analyst intern at CloudSec, and I love to play the drums and play football. Yep.
Cool. So let's move on. Yeah, so the agenda of our talk is basically divided into 3 parts. In the first part, we are going to explore what exactly happened with the unicorn that we're talking about. In the second part, we will talk about how we analyze and find vulnerabilities in mobile apps. And in the end, part 3, we are going to talk about a large-scale study we did of over 1 million plus apps and the impact. So moving on. Let's begin with part 1. The next slide, please. Yeah, so source code leaks have been in the news for many years now. And the biggest one that comes off the top of my head is the recent Twitch leak that happened in 2021, where we saw that malicious actors posted on the 4chan forum over 6,000 internal Git repositories of Twitch, which contained 200 GB worth of data and 3 million documents. So just by the scale of these numbers, you can understand how big this leak was. And earlier this year, we did a little something of our own, which we'd like to share with you guys. So moving on. Let me present to you the big fish. So it was a casual work afternoon for us. We were just doing our normal thing, analyzing top apps and finding security vulnerabilities in them and reporting them to the organizations. So what we found was really interesting. We found that there was this app which had 10 million plus downloads in Play Store of a 120 million worthy unicorn that had a really big security vulnerability with which we could basically view their entire source code and do a lot more things with it, which we'll tell you in the coming slides. Moving on. So let's explore what exactly happened. So what happened was that while exploring the code base of this app, we were analyzing it on this search engine that we built. And what we saw was that there was something called as a GitHub personal access token, which was hard-coded into the app's Android bundle file. And it was there for everyone to see and do anything with it. So that's not exactly desirable, especially not from a unicorn. A lot of questions might be arising in your head. People might be asking, what is a GitHub personal access token and what can a person do with it? So we'll explore that in the next slide. So a GitHub personal access token is basically an alternative to using passwords for authentication in GitHub using the GitHub API or the command line. So with this token, basically, you get a lot of privileges, and we ran this query, as you can see in the screenshot on the screen. What happened was that we passed the GitHub token that we found in the previous slide, and we wanted to explore what scopes is this GitHub personal access token giving us. And you can see the output in the screenshot. We could see that we're getting admin privileges. We could delete the repo, we could delete packages in the repo, we could change the workflows, we could write packages, we had the repo scope, we had the user scope. So out of all of these scopes, the most important is the scope repo, which gave us full access to the private repositories. So just to give you an idea of what we could do with this scope was, basically we could commit changes to the organization's GitHub repo and push them. We could also invite other collaborators and ask them to do the same. We could mess around with their deployment workflows. We could delete their repo. Basically, in the end, to sum it up, we could do anything with their repos with this scope, with just this scope. And that's a pretty big deal. Now, moving on to the next slide. After finding out that we could get access to the private repositories, we wanted to see how many private repositories can we actually get access to. So we ran this query that is shown in the screenshot. We passed the token against this endpoint, and we were able to find that we could access the organization's all 26 private repository. And that's the impact was pretty nasty. So moving on to the next slide. And this is what the private repositories URLs looked like. So you could conclude that we could get access to the Unicorn's iOS apps, their APIs, and their normal Android mobile apps. Finally, this is how we got access to the Unicorn's code base. So after finding this issue, we immediately reported to the company, and they acknowledged the issue and fixed the bug. And the token is now no more there. Moving on. So let's count the mistakes. So how are we able to do this entire thing? There were two major mistakes that were on the developer's part. First mistake was hard coding the GitHub path token in the source code in the first place. So once we found that hard-coded GitHub path token, we could clone their repos on our system and just view their code base. So till now, we are just able to view the code base. But where things went really south was mistake number 2, with which they gave excessive scope to that token, and anybody could use it for exploitation. Like anybody could commit changes to their private code base. Anybody could invite other collaborators and change the entire organization structure and whatnot. So these were two really big mistakes that they made on their part. Now, the talk is titled "How we analyzed, how we got access to a Unicorn's private code base by analyzing millions of apps." So surely millions of analyzing millions of apps is basically not, it's something a person cannot do manually. It's a Herculean task to do manually. So we automated this process and we did a lot of analysis on our part. And I'd like to give it over to Arshit, my teammate, who's going to explain about this part a little more in detail. Arshit, I believe you're still on mute.
Hello. You can hear me,
Yeah.
right?
Yeah, we can hear you.
So till this point, many questions would be arising that how did you start scanning the code base of this app? How did you reach to the secret at the first place? So let me tell you a story. One day, our security team, out of curiosity, were doing a study on secrets that can be found on GitHub public repos. And to our surprise, we found there were many secrets that people have just hard coded in the public repos, like Stripe keys, Razorpay keys, AWS credentials, and assets like Firebase URLs and AWS Cognito URLs. So this was like a big mistake that developer have done on public repos. So then we thought these are public repos which anyone has access to. So what about the source code that no one has access to, like mobile apps? So then after doing some initial research, uh, we did not find any good tool that can just like tell us about secrets that are being leaked across the mobile app. So then for analyzing the mobile apps, we build our own security search engine. So here are the steps that we followed to build this mobile app scanner. So first was we collected the data. Second step was we decompiled the apps that we collected into readable source code. Third was we created a set of rules of regexes, so to identify the hard-coded tokens. And the third was to build a interface where we can just do a regex or like keyword search, and it will return you all the results on all the source code that we have collected. So let's deep dive into all the steps that we followed to build the system. So the first step was collection of mobile apps. We thought, can we build a system in which people can just come upload their mobile apps and they can get their security reports uh, and just know the secrets and issues in their mobile app. So user submission was the first source that we collected the data from. The second source was we collected the Android apps across the internet. So that included apps that were being downloaded from Play Store and as well as third-party app stores. So while we were crawling the Play Stores, we faced many difficulties, like sometimes we were not able to download apps from certain countries, or sometimes there were issues like some apps were not compatible with certain devices, but we were able to overcome all those problems. And the reason we downloaded the apps from third-party app stores was because we wanted to analyze the fake apps that have been wandering around on these third-party app stores, because these apps on third-party app stores contains malwares, or sometimes people have just tampered the certificate and uploaded the apps in the system. So currently we have about 1 million apps that has been indexed in our system. So after collecting the mobile app, we thought let's like decompile those apps into a readable source code. So to do that, we used an open source Android tool called ZX. So ZX, it helps you to decompile Delvic bytecode into Java classes from APK and DEX files. It also helps you to decode Android Android manifest XML file. So after decompile all these apps, we thought we stored all these apps into a file system. So while we were storing these apps on file system, these apps size is like app size get increased due to like many things that are there in these apps. So we did some optimization on that part as well. So after decompilation, we thought let's how do we find the secrets on these source code that we have. So for that, we started building regexes that can be found on the source code. So for building those regexes, we thought let's like maybe analyze some mobile apps and see what kind of keys usually do developer use in the mobile apps. So after this, we started building the regexes, and there were many difficulties that we faced while building those regexes. Like sometimes the length of the key was not fixed. Other time we were not able to even find the regexes for it. So for those for which we did not find the regexes for, we went to open source repositories like i4thun and Truffalog. After we had all the regexes in a place, we took all those regexes, or we took all the keys and just put up all the keys in an Android file. Uh, so apart from putting it specifically in a class, we put it all the keys in Android.manifest file, Java classes, and then after putting all those keys, we compiled the Android app, and we put the Android app through our system so that we can see whether we are able to detect the particular key or not using our regexes, and that also help us minimizing the false positive. So after collecting the apps, decompiling it, and building the regex for all the keys, we went and we automated the process. So we wanted to provide an interface where people can come, just do a keyword or reject search, and it will just list out all the results that we found using our source code. So, and this is how we were able to reach to the unicorns GitHub token using the regexes that we built for a Gitpat token. So this is this is only the one use case that we found where using a GitHub Pat token we were able to reach unicorns private code base. So imagine what can happen with all other keys that are hard coded in the source code. So let me call Manan on stage. He'll give you the insights of impact of these secret leaks and why do developers do such mistakes.
Well, let's take a deep dive into GitHub PATs. So we were able to find 159 private repositories from 151 GitHub tokens that we found by analyzing mobile apps that had installs ranging from 100 to 10 million on the Play Store. This may lead to leaking of secrets like database configurations, which in turn lead to decline in brand confidence and imminent financial losses. By the way, all organizations involved with the above leaks were informed of the same and corrective measures have been taken by them. Well, we can lie, but numbers definitely won't. Till now, we've been able to find over 1.6 million hard-coded sensitive tokens. As you can see in the pie chart, some of the prominent ones are Firebase and AWS readable writable buckets, Dropbox API keys, Facebook secrets, etc. Now that we materialize things a bit by seeing the enormous number of leaks and move ahead of the abstract part, let's now take a delve into the impact of these keys and what malicious actors can do with them. The best way to make you all feel the intensity would be to take you through some examples. Well, let's take up email automation first. There are email automation services like SendGrid, MailChimp, Mailgun, etc. Let's analyze what happens when the secret token for one of these services gets leaked. The attacker gets access to read and send emails from all the accounts associated with that particular key. Using this key, the attacker might be able to start a phishing campaign from the official mailing channels of that organization, which generally would be trusted by the customers or the consumers. Also, the attacker might be able to gain sensitive and personally identifiable information like names, emails, contact numbers, etc. of those customers. Similarly, if the attacker gets access to tokens for services like Razorpay, Stripe, etc., which are payment processing tools, they might be able to do very nasty stuff that might tarnish the reputation of the organization and further cause financial damage as well. Other than that, they might be able to gain access to transaction details of the customer and organization, like credit and debit card information. Well, now I think all of you would have gotten a gist of how frightful the consequences of such leaks are. Therefore, it would be a good idea to talk about why developers do this. Well, to be able to answer this question in a succinct manner, we'll have to look at some common problems faced by Android app developers. We all know how much of a pain it is to focus on building security and CI/CD pipelines instead of building the actual application and have diverge efforts. Other than that, there is an issue of awareness. Many developers think that it is okay for them to leave hard-coded tokens in their source code as it is going to be compiled into an APK before publishing. But as a cybersecurity community, it is our job to make them aware that such is not the case. Also, companies can sometimes feel that money is better spent in other domains rather than spending it on proper security testing on their mobile apps. One example would be an app called Clubhouse, which became very popular, but it didn't implement end-to-end encryption on their RTC packets, thus any attacker could perform a man-in-the-middle attack and snoop on private conversation. Well, now that we've discussed the problem, let's go through some of the solutions for the developers. Scoping is the most primitive method of stepping up the security of your app. You can do this by assigning the secret keys only the necessary permissions so that even if the attackers get access to that key, the damage is controlled and limited. Using of environment variables to store keys is another solution so that they're not hard-coded in the code, but rather embedded into the operating system and relatively out of the reach from the attackers. Other than that, making use of Git hooks like Husky to prevent yourself or anyone in your team to even push secrets by mistake. Also, you can make use of vaults like HashiCorp Vault to safely store all of your secrets. Most important of all is building a very robust security pipeline so that your application is secure from development till the time you publish it. Now, I would like to discuss some of our future plans. Till now, our research was more centered towards Android applications, but in the future, we aim to expand our scope to include client-side JavaScript and iOS applications as well. Lastly, I would like to mention a tool, which is the BVigil OSINT CLI, developed by us so that the community can leverage the asset data extracted after analyzing millions of mobile apps. If you want to try out for yourself and see the security score of any mobile app currently installed on your phone, we would encourage you to go to bvigil.com and search for the app there. As you all know, that the first steps towards change is awareness. With that thought, we invite any questions that the audience might have.
Okay, wonderful. Thank you very much. Very interesting talk. Any questions? Just come in front here and ask your question. They should be able to hear you. They are far away, they can't bite you. So I know everything about the project. Okay. So still, thank you very much for the question, for the talk. And do you have any contact information? Or there should be contact information on the website if you have any additional questions. Thanks a lot and enjoy the rest of the day.